Good morning, students.
Good morning, sir.
Are you ready for day 3?
Yes, sir.
How do you feel about it?
Super duper, sir.
All right, let's go. So today we are going to be taking waves.
Yes, sir.
Practically everything that you need to know about waves. We'll go from waves, introduction to waves, light waves, that is optics, electromagnetic waves, and application. So in order to assist us to move fast, we are going to be moving at the speed of light because we are studying light today. Is that okay? So in order to assist us to go fast, we're going to take these two first, then these two, and then these two. Are we good?
Yes, sir.
All right, let's go. Waves. Somebody say waves.
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 All right. All right. So what is a wave? Yes. That's made of the source of hair that transfers energy. All right. So let's go now. A wave is a disturbance that is created at a point and transfers energy from that point to another, but without the permanent displacement of the source of the body of that point. Is that okay? What did we say again? A wave is a disturbance. First is a disturbance, yes. Yes, made at a point, and transfers energy. So the basic thing about it is what? Is a disturbance and it transfers energy to another point, but without the permanent displacement of the body or the source. Is that okay? So for example, just like I'm speaking now, I am moving my lips and I'm distorting air, but this air is not what is moving to your ear. It's not the air that is closest to my mouth that is moving to your ears. The air will get vibration from my mouth, right? And transfer it to the next air layer, transfer it to the next layer, and like that, until it gets to the layer of air in your ear, and that's why you're able to hear me. Is that okay? All right, so that's basically what wave is. Now let's go to classification of waves. So what are the classifications of waves? Classification. Okay, we can divide wave primarily into two, right? So we have the standing wave or stationary, right? Stationary waves, and we have the progressive waves. Now, under the progressive wave, we'll have another two. Now, what are the two waves we have under progressive wave? We have what? The transverse wave and the what? Longitudinal wave. Okay, basically, what are standing waves or stationary waves? Waves that have two fixed points, right? They have boundaries, two boundaries, so they cannot go beyond that boundary. Is that okay? So they have a source and an end. Of course, they can return to that source and still go forth and back like that. But of course, they are fixed. That's the meaning of standing wave. And an example is what? Sound wave or wave in musical instruments. Do you remember? All right. Then progressive waves. Any wave that just has a point source and can continue. Is that okay? So you remember that most of our waves that we draw, we just draw one line here, one position of, or the source, and then it just continues like that. All right. So those are progressive waves. Now, the transverse wave or longitudinal wave. Now, what is a transverse wave? A transverse wave is a wave that travels in a direction that is perpendicular to the what? The source that produces it. So the direction of travel of the source will be vertical, for example, but the direction of travel of the wave will be what? Horizontal. Does that make sense to us?
Yes.
An example is water wave. That's a very typical example. If I throw stone inside this water, what will happen? The stone will go. If the stone will sink, of course, right? When the stone gets here, it touches water, it goes down. Now, as it is sinking, it is moving down, right? But you see ripples move in what direction? This direction and this direction, right? So you see that's what 90 degrees to each other. Does that make sense? So that is transverse wave. The wave travels in the direction that is what? perpendicular to the source that produces. Good. Now, then another kind of transverse wave is the light wave. The light wave is produced by, the light wave is one of the electromagnetic wave spectrum. Do you remember? It's produced when the electric field of the earth and the magnetic field of the earth do what? They intersect at 90, they interact at 90 degrees to each other. Then you make what? A transverse wave. You get light wave. I'm going to explain what light is, essentially, under electromagnetic waves. Then what's a longitudinal wave? Longitudinal wave is one that does what? Travels just in the direction of the body that produces it. Is that okay? Or in direction parallel to the distance that produces it. An example is a sound wave. Now, one thing that differentiates them is this. Transverse wave can be plane polarized. Transverse waves can be what?
Plane polarized.
Why these guys cannot be what? Plane polarized. In fact, they need not be polarized. Do they need to be polarized? No, because they already travel in one direction. But these guys, transverse wave, they are traveling in what? Two different directions. So if you want it to travel in a particular direction, you polarize it. You turn it to one direction. Is that okay? And what do we use to polarize? We use polarize. Okay, when we get there, I'm going to talk about it. Now we have the transverse waves are divided into two. Is that okay? The transverse waves are divided into two. Why this longitudinal wave is divided into only one, or it has one subunit, which is what? The mechanical, with the what? The mechanical wave. And an example is the sound wave that I've talked about. Now, the transverse wave is divided into two. We said you have the EM waves and the what? Mechanical waves. Now, the EM waves, what are EM waves? Waves that are electromagnetic waves, right? I said they are produced when the electric field and magnetic field interact at 90 degrees. Okay. Then mechanical waves, they are waves. Okay, the way we define them is that mechanical waves are waves that require what? Material medium for propagation. It means they need an entity, they need matter to travel. Does that make sense? They need matter to travel. So more like they are not, okay, waves generally are not particulate. Is that okay? So, but this one, they need particles to actually travel. Do you get it? And an example is water wave. No, sound wave will not be under here. Does that make sense to you? Sound wave will be under here. It's a mechanical wave. Do you understand? But an example of EM wave is the light wave. Light wave is not mechanical. Why? Because it doesn't require material medium to travel. If you want light in travel, if you want light in a vacuum, vacuum means a space that the air has been withdrawn. So there's no air there. If you on light in that vacuum, in fact, light will not travel the fastest. Do you remember that we said the speed of light in air is what? In vacuum is what? 3 by 10 to the 8 meters per second. Do you get it? So light travels in vacuum, but sound cannot travel in vacuum. We've talked about that, right? That if you have a bell there and then you extract. So that's the case. All right. So these are the classification of waves. Is there any other one? No, right? Okay. Now let's now talk about the terminologies that we use to describe wave. The terminologies we use in describing wave. So number one is or should we first talk about the characteristics of waves? Let's talk about the terms. Terminologies. Okay. Now the first terminology we are going to talk about is the let's talk about amplitude first. Amplitude. So now a simple waveform looks like this. Okay, now first let's talk about the fact that a wave has this essential property of circular motion that is equal to that of a body in circular motion. Is that okay? So that it can be represented by a sinusoidal graph. Can be represented by what? So for example, the reason why this wave takes this form is that its motion is just like the motion of a body in a circular path. All right. So, and we have talked about the fact that that is the way it just happens. Is that okay? But the point is this. So, the way we analyze for circular motion is the way we are going to analyze for this guy. Is that okay? Now, the amplitude of this wave is the highest upward or maximum displacement. No, let's first label this guy. Now this guy is called what? Or vertical displacement. Does that make sense? Vertical displacement. I'll call this one what? Horizontal displacement. Does that make sense? Okay. Now, the maximum, okay, this point here on the wave is called the crest. It's called what? And this point here is called the trough. Okay. Now, the maximum vertical displacement upward or downward is called what? The amplitude. God bless you. It's called the amplitude. That's the maximum upward or downward displacement. That is the amplitude. Okay. Now, let me just quickly use this guy to describe some things. Now, you see this guy as it is now. He's going to his office. Now, you see this guy as it is now. A cycle is this, right? Good. A cycle is, I tried to show you how that this is the case, right? That is circular wave. Do you remember we were saying if this body was moving like this is circular, right? If I brought it to your frame, if I made the frame of your frame of reference to be such that you can see it only in the horizontal view, what would you see? Back and forth movement, right? And I think I showed you with the fact that if I'm going up and down, up and down, up and down, up and everybody up and down, up and everybody up. Okay, so if I was going up and down and I displaced one of the frames, such as either this guy or this guy, you get this waveform, right? Okay, I was supposed to talk about this first. So you see that I did not stop moving up and down, but I have gotten this, right? Okay. Now, and you know that up and down is just the circular motion too, right? Okay, God bless you. So oscillatory motion, circular motion, wave, you are seeing the relationship, right? Okay. So I now said that a cycle in a waveform is the distance from here to here. It's called what? A cycle or a complete revolution. That makes sense. Let me make sense of it for you. So, want to draw a cycle? We go to the first quadrant, the second quadrant, so we've completed half of our journey. So we go again, this third quadrant, then the last quadrant. Do you see that? That's a cycle. So the same way, let's do that here. First quadrant, second quadrant, third quadrant, fourth quadrant. So this is called what? A cycle. Is that okay? Or a wavelength. It's called one cycle or one wavelength. Another definition we give wavelength is the distance between two successive troughs or crests. So two successive troughs or troughs means two crests or troughs that are following each other. So for example, the distance between here and here will be what? A wavelength. Does that make sense? The distance between here and here will be what? A wavelength. All right. Now another thing is, now the rate at which a cycle is completed, is called what? The frequency. I've told you rate means you are dividing by time. Do you remember? Whenever you hear rate of something, what does it mean? You are dividing by time. So the rate at which a cycle is completed is what? The frequency. So let me ask you a question if you have understood what I just said. Which of these waves will have the highest frequency? These waveforms. Look at this one. Okay, now, so describe waveform A, B, C in order of frequency. Describe them. Which one? In order of frequency, in descending order of frequency. From the highest to the lowest. So arrange them in descending order of frequency. BCA, that is correct. Do you understand now? Because if you look at it vividly, this one is completing the first, provided they have the same, they are defined by the same parameters. Say, for example, we are using amplitude against time, for example. We're using amplitude against time everywhere here. It means that this guy just completed a wavelength here, right? At that time, what is this guy completing? About almost 10 wavelengths. Do you understand now? Is it clear? Yes. If you bring this guy down here, this guy has completed about 1, 2 and a quarter, right? So why this guy has completed more than that? So this guy is going to have the highest frequency. This guy will have the next frequency, then the lowest frequency. So each of these waveforms correspond to a person. Which of these waveforms can represent the waveform of the voice of the sound of a person that has bass voice? Correct. God bless you. Do you understand now? It means that because God bless you, God bless you. So which one will correspond to someone that has soprano?
I don't know how soprano sounds.
Okay, don't worry. Yeah, something like that. That's going to be B. Soprano is the highest. What's soprano? Is that not the highest, tiniest voice? Tenor, I don't know. Leave that one. At least we know the highest and the lowest, right? Okay, so that's frequency. Now, what is now a period? The period is this. So, let's now go. Let's go. We have defined the following. We said amplitude is what? The highest maximum upward or downward displacement, right? Is measured in what? Meters. Do you remember?
Yes.
All right. Good. Now, the next thing is the frequency, or no, let's talk about wavelength first. Wavelength is what? A cycle, right? Wavelength or lambda is also measured in what? Meters. Is that okay? Denoted by lambda. This one is denoted by A. Does that make sense? Capital A. Now, this wavelength is a cycle. The distance of one cycle is going to be the wavelength. Okay? Then the frequency we said is what? Frequency is denoted by F, right? Frequency is the rate at which a cycle is completed. The rate of completion of cycles. Okay, is that okay? Then we now use the formula that it is the number of revolutions or number of cycles, number of revs or cycles completed per time. Does that make sense to you? All right. Then so it can be measured in what? Rads per seconds. Do you remember that? Okay. Now another thing is the period is now the time taken to complete one revolution. That is time per what? Per revs. God bless you. Per number of revs. Per number of revs or cycle. So what does it show you? The period and this are related by as inverse of each other, right? So we say that frequency is equal to 1 over t, or period is equal to 1 over frequency. Does this make sense? Okay. Now the next thing is we talked about frequency. Let's talk about what else? Velocity of sound. Now, what's velocity of sound? It's just what? More like it has the normal definition, which is what? Distance traveled by the wave over time. Is that okay? Distance traveled by the wave over time. But this also, now look at this. Now the distance traveled by the wave is given by how much wavelength, are you with me? Per time. Does this make sense? How much wavelength is completed per period, rather? Is that okay? Okay. So if this is the case, remember that 1 over time, 1 over period is what? Frequency. So that becomes what? V. So our formula becomes what? V equal to what? F lambda. Do you understand this? Does this make sense to all of us? It does make sense to you. Raise your hand. Okay, we are kicking. Now, so that is the formula for wavelength. Now, if it was for light, to be C equal to, so we represent by V for normal other waves, and represent by C when we talk about light. Is that okay? Speed of light. So, but it's still F lambda rather. F lambda. All right. HF came to my mind. What formula is that? Planck's constant, energy of a wave, of a particle. All right. Now. How about phase difference? Have we talked about phase difference? Let's talk about phase difference. What's phase difference? Denoted by what? By phi, right? Okay. Measured in rads or radians or degrees or. But the one I told you, I said you should try to be measuring. Okay, first, master this formula that it is phi is equal to what? 2 pi x over lambda. Now I have taught you how this was gotten, right? Okay. It's not like you're actually cramming anything. It's just a fraction of the wavelength times one cycle. Do you get it? All right. But maybe I'll link the video in the description where we talked about how it was generated. But for now, you can cram it as 2 pi f over x over lambda. This helps you to be able to convert your wave, whatever this thing you are solving for, into the proper dimension. This thing you are supposed to give it in units. So, for example, if I have a waveform like this now, if I have this waveform, and I have here denoted as A, B, C, D, E, F, G, H, I. Now look at this waveform. It now says find the phase difference between points. Give me points.
Point A and F.
Now don't worry now.
C and I.
C and I. No, you've been giving me no. B and G. Mm-hmm.
C and F.
C and
H, A and I.
C and what?
C and F.
C and F.
A and
A and
I. F and H.
C and H.
F and C.
C and H. Let's stop at this. Let's just do this 4. Is that okay? Okay, so very simply, what you will do is this. If I want to find the phase difference between A and F, you will say phi is equal to. Now, watch what I will do. The first thing you should know is this. If I want to analyze my waveform with, there are 2 ways I can analyze. 3 actually. I can analyze by wavelength. 1 is that analyze using wavelength, or I analyze using pi, which is the best, and I analyze using degrees. Is that okay? Theta. Okay, so if I want to analyze with wavelength, you're going to see that why this one is easier now. So if I had something like this, for example, how many cycles are here? How many wavelengths are here? 1, 2. Does this make sense?
Yes, sir.
Okay, so I'll say that the phase, so if I want to analyze the phase difference, it means from here to here is a wavelength, right? So if from here to here is a wavelength, from here to here will be what? So if this is lambda, this will be lambda over 2. That makes sense, yeah? Now, if this place is lambda over 2, what will this place to this middle be? Lambda over 4. What will this place to this place be? Lambda over 8. Does that make sense to all of us? Okay, that means that this place will be what? Just add 1 over 8 here. Do you understand? So the shortest distance here with wavelength is what? Lambda over 8. Does that make sense? All right. That's how to analyze using wavelength distance. So if I want to, for example, okay, so I'll be solving maybe one of the questions using this method, but I prefer this thing, the phi. I think the phi is easier, and you're going to like it too. So what's this? Okay, so we still have 2 wavelengths here, right? We're not analyzing with that. Analyze with this now. So the pi, how many? From here, 360 degrees, how many pi? 2 pi. We know this, right? Good. So once you know that, then your problem is solved. From here to here is a cycle. We already know that. So this is 2 pi. What will this place be? Pi. Does that make sense? Half of 2 pi is pi. Okay. So from here to here, which will be what? Pi over 2. God bless you. Then from here to here, the shortest distance what? Pi over 4. Is that okay? It doesn't mean that we cannot get points between here and here. I'm just saying those are the possible questions. Is that they ask you this point or this point in that degree. Is that okay? Okay? Or in that order of value. Right? So, what will this place be then? 3 over 4 pi. Because it's a quarter. So, just take it in quarters. Is that okay? So, you want to take it in quarters, you have. So, you take it in quarters like this. 1, 2, 3, 4. So, it means that inside one dome. I'm going to have 4 quarters. Does that make sense? Okay. One of the reasons why I say she use this quarter is because when we get to sound wave, I mean pi rather, is because when we get to sound wave, it's also going to help you. Anyways, all right, let's go on now. So it means that from here to here is 180, which is pi, right? So pi is 180. Does that make sense? Okay. And you can further, continue. You can say this will now be from here to here, now what? 1 number 1 over 4 pi. Does that make sense? Here will now be what? 1 number 1 over 2 pi. You get what I'm doing, right? Okay. So what if we wanted to analyze in degrees? In degrees directly. The answer is most likely to be given in degree or pi. Okay. So I have this waveform still. So let's analyze in degrees. In degrees. So from here to here is 360 granite. Does that make sense? Here is 180 granite. Here what? 90 granite. Here what? 45 granite. And that makes sense because 45 times 4 is 180. So that's why it's the same. They're almost the same. They're basically the same. Only that I just want to use numerics directly. Is that okay? So you can just say 45, 45, 45, 45, 45. It's the same. Only that your answer, if you are giving your answers in this, you have to know how to convert back. But you are giving in this, you can easily do it. I'm going to show you how to go about it, okay? So let's go to doing A and F. Let's go and do A and F. Let's see the distance between them. Between A and F, that's one wavelength, right? So the phase difference for A and F is going to be what? 2 pi or what? Lambda or what? 360 granite. Are we good?
Yes, sir.
If you don't understand, raise your hand. Okay. Okay, number 2. The phase difference between B and G. B and G. Let's see. That was a wavelength now. Distance between 2 successive crests and 2 successive troughs. Is that okay?
Yes,
but if you don't know what I did, it's very simple. Just say that from here to here, the words a quarter pi, right? Does that make sense? Now we're doing pi. Good. Now this will be a quarter pi. So let's see how many quarter pies we are going to have. 1, 2, 3, 4, 5, 6, 7. So no. 1, 2, 3, 4, 5, 6, 7. Yeah. Are we correct? We're not correct. Yes, we missed this part. Did you get it? So don't make mistake. 1, 2, 3, 4, 5, 6, 7, 8. So that becomes what? 8 pies. 8 pi over 4s. Does that make sense? We saw how many pi over 4? 8 of them, right? So 4 here 1, 4 here 2. So the answer is what? 2 pi. So that still makes sense, right? So 2 pi or lambda or 360 granite. And if that's confusing, just use your guide directly. Okay, your definition rather. C and F now. Let's go to C and F. C and F, let's see. From C to F. That's what? That's 360 divided by 2. That's what? 180. So phase difference here is going to be what? 180 granite or pi or lambda over 2. Does that make sense? Then IV, the last one. Distance between phase difference between C and H. That what? This is almost a circle, right? A circle minus quarter. Does that make sense? So that would be like 2 pi minus pi over 4. What would that give you? 1 number 3 pi over 4. Does this make sense? Is it clear? That becomes what? 7 pi over 4. Now if you want to convert this to, let's say, degrees, just multiply by what? This guy here now is your what? It's 180, right? So just multiply by 180. Here 4 here 1, 4 here 45. 45 times 7 will give you what? 315. 315. And that makes sense. 315 plus 45 is what? 360. Are we good?
Yes, sir.
Are we good? Okay, let's go. Now, there's something called. Now, if you say two things, two points are in phase, let's talk about being in phase here now. Because there's phase difference and being in phase. Okay? Now look at this wave. Now, if I say point A, B, C, D, E, F, G, H, I, J, K, L, M, N. Now, which two points are in phase here? Do you agree with me that points A and C are out of phase? Are they out of phase? Okay. Point A and F, they are in phase. Do you agree with me? If you don't understand, raise your hand. Okay. Look at it. It's very simple. They are in phase means that they are the same portion of the wave. They are the same what? Or part of the wave. So for example here, A is at the start here, right? Yes, which other one is at the start? This one is at the finishing of the first circle, half circle. So F is also at the start of another circle, right? So they are in phase. A and F are what? In phase. Does that make sense? How about which one again? B and H, are they in phase?
Yes, sir.
Yes, they are. Anyone that is on the trough and on the crest, they are in phase. Okay? D and M, are they in phase?
Yes, sir.
D and M. Okay, let's look at it. D is on the descending part of the wave. M is on the ascending part of the wave. Is M in this middle here? I think it's even here. Okay, if I put something here, let's call M sub X. Is on the ascending part of the wave, so they are not in phase. Does that make sense to you? Is this a confusing someone? Okay. E and J, of course, they are not in phase, right? Okay. K and D, are they in phase? Yes, exactly. Exactly. Okay. So do we understand? G and I, are they in phase? No, but they are they're on the same side now. Okay. God bless you. Do we understand now? All right, let's go to characteristics of waves. Let's go to what? Characteristics of wave. Let's go to character. Let's go. X6 of waves. Is it X6 of properties? Yeah, is it not the same? Are the same, yeah? Okay, number one, the first property of wave. Now, all of these properties appertain with, or at least most of these properties appertain with all the waves that we're going to be discussing. Is that okay? Except a few of them, such as polarization, that is not associated with sound wave. Polarization is not associated with
Sound wave.
Why? Because sound wave is a what? Exactly. Why is polarization not associated with it? Sound wave is what? A longitudinal wave. So it cannot be polarized. Okay, number one, let's talk about reflection. Somebody say reflection. Okay, now what is reflection? Reflection is, you might see the change in direction of a wave when it strikes an obstacle, or the bending of a wave when it strikes an obstacle. Either way you say it. Now this is what happens. So if we, now for most of our analogy, we'll be using sound wave and light wave, which are the ones that we'll be considering the most. Is that okay? Alright, so if a ray of light strikes a particular point, it is going to bounce off that surface, provided that surface is not, provided that surface does not, it doesn't transmit it. Is that okay? Provided that surface does not what? Transmit it. That surface will be called what? Opaque. That surface will be called what? Opaque. Okay. So what will happen is that this light wave will now travel in the other direction. So we'll call this the incident ray. We'll call it what? Incident ray. And this way that is going off the what? Okay. Now, the angle at which they are incidenting or reflecting will be measured with respect to the what?
A normal.
To a normal here. Now, for those of you that usually don't understand what a normal is, a normal is just any line, any plane that you make perpendicular to a particular surface. Is that okay? That's why when we're doing inclined planes, I told you that the weight of the body will go down, right? But normal reaction is the normal to this plane. Does that make sense? Okay. Somebody say okay. Alright, let's go. So now the angle of incidence is going to be the angle here. The angle of reflection is going to be the angle here. Now there is a law of reflection that says that the angle of incidence and the angle of reflection, they lie on the same plane. Do you see that? And also the angle of incidence is always equal to the angle of, for what? A smooth plane surface. If it's a rough plane surface, it will give you what is called diffused rays or diffused beam of light if it's more than one. Okay. The path taken by a photon of light is called what? A ray. Is that okay? So that ray, if it comes in many, what we don't see a ray. What we see is a beam. No, me, I can see a ray, understand? But what we see is a beam. Do you understand? So a beam of light that is incident on a plane surface will produce you a perfect beam too. But if it's incident on a rough surface, to produce what? A diffuse, scattered beam. Does that make sense? Okay. So we are done with reflection. When we get to reflection in other ways, we'll talk deeper about it. Now the next thing is refraction. So what do you say? Refraction. All right. Now refraction of wave is what? The change in direction of wave as it moves from one medium to another, provided they have unequal optical densities. Do you understand? When ray of light moves from one medium to another, and those two media have different or dissimilar optical densities. That is, one is more optically dense than the other. You don't understand optical density, right? Optical density means how much it allows light to penetrate, or how much easy it is for it to transmit light. Is that okay? So that is optical density. So for example, when we are sending wave from air into water, are you with me? Which one have more optical density? No, more optical density. Water will be more optically dense. Is that okay? So how did I define optical density? I said how much, yes, it's a measure of how much it allows light to be transmitted. So air allows more light to be transmitted, so it will have low optical density. Is that okay? Air transmits light easily, faster. Is that okay? So that's why the speed of light in the air will be greater than speed of light in. Does that make sense now? And that's why the depth of the sea or ocean is usually what? Dark. Do you understand? Usually what? There's a layer, a level there that is called abyssopelagic. Abyssal zone mean abyss. What does the word abyss mean? Abyss means bottomless, endless pit. You get it, right? So abyssal zone. You get that? What that means now here. There's even one that is called the hydropelagic. That one, Hades. What does Hades mean? We are saying someone has gone to Hades. The person has gone to hellfire. You get it, right? So they now name a part of the ocean hydropelagic. You get it now. Usually, in fact, in hydropelagic, you see, this thing of ocean is like this. Is that okay? Something like this. So we call this place, they have names, is that okay? We call this continental shelf, continental slope, and continental rise. So this place around here is the abyssal zone. Then this one here, we call it the oceanic trench or hydropelagic zone. So in this zone here, in fact, volcanic eruption occurs. Volcanic activities basically occur here. So it's like going from cold to heat. You see how very, whatever. So my point is that this place, you can't see anything. That's why the organisms here are bioluminescent. They are what? And we're going to talk about that when we get to light waves. Okay. So I said what? That light wave that is incident on this guy, we are going to erect a normal. So this is our incident ray. By the time it touches this surface, it will not go straight downwards. Do you understand? Okay, I didn't mention something here. It's going to bend in a way. Is that okay? So what does that mean? It means it has done what? Deviated from its path of movement or direction of movement. Does that make sense? And we can calculate the deviation. Is that okay? So this deviation is called refraction. It's called what? And don't confuse it. We denote both reflection and refraction with R. Is that okay? So refraction is when it's going into from one medium to another. All right. So let's go to the next one, which is what's the next property of wave? There is also deviation in this guy for reflection. So, for example, if I have a ray like this, it should be going like this, right? It now goes like this. So the deviation is going to be what? From here to here. Do you understand? That's deviation. Okay. Deviation means where it's supposed to go minus where it's going. That's what I just said. I said it has deviation. No. That's refraction, right? I said, see, this refraction, right? To bend. Does that make sense? So it deviated. This way is supposed to continue, right? But it deviated to this place, right? In this place, it goes like this. It goes in that other direction, right? It's also as it's coming like this, it's supposed to continue like this. So it means that it deviated to this point. So both of them have deviation. Do we understand? All right. Now, somebody said now. Okay, the next one is diffraction. Now, diffraction is this. Diffraction is when the ray of light wants to permeate an open slit. So if it encounters an obstacle in its direction, are you listening to me? If it encounters an obstacle, what it tries to do is it tries to bend. Do you understand me now? It tries to do what? Bend. So if I have a beam of light now going like this. So by the time they get here, they should strike here. Some will be reflected here, right? But you see these ones that are that will pass through this slit, they will be diffracted. Is that okay? They'll be diffracted in a way. A diffraction is best seen with even sound waves. So that's why if you are someone that is at the back of this place, if you are playing a music this here, and then it's shouting, he's making noise. Boom, 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 boom. Although the volubility here or the what's it called? The intensity here will be lower, but you see here. Do you understand? It means the sound will bend to meet the person. Is that okay? All right. So that's called what? Diffraction. So the bending the way of light because of an obstacle is called what? But the bending of light because of optical density is what? But the bending of light because of an obstacle that it cannot permeate at all is what? Good. Okay, now there's another property that is called interference. Somebody say interference. Now, interference is basically is a phenomenon that occurs when two waves that are either traveling in opposite direction or traveling in the same direction, they interfere, they move together. Is that okay? That's interference. In sound, we are going to be studying beats. I'll just mention beats briefly. So it's what creates beats rather. Is that okay? The peaks of two waves that interfere. There are two types of interference. Interference talks about the superimposition of wave. What do I call it? So for two waves, there are two principles of superimposition. For two waves to interfere or to be superimposed, the two waves must have coherent sources. Is that okay? Now this is the point. If there are two types of interference first. If there are two types of interference, I said destructive and constructive. Is that okay? Let's do constructive first. Constructive interference and destructive interference. Now, in constructive interference, Constructive interference is the one you see when the amplitude of one wave adds up with or is in sync with the amplitude of another wave. Is that okay? So those two amplitudes, they will do what? Come together and create a higher amplitude. Does that make sense? The two amplitudes will mix together and will create, if one was coming like this, for example, let's draw a wave that is going like this now. And let's draw another wave that is coming like this. So you see that the amplitude almost cohere, right? Do you understand what I'm saying?
Yes, sir.
Or is either the amplitude cohere perfectly or almost cohere. If they do, what will happen is that they are going to create a larger amplitude. Is that okay? Than the one with which they had. Is that okay? Then a destructive interference is one that happens when the two waves that are coming together, the one has a trough, a crest, and the other one has a crest, and the two cohere perfectly. Is that okay? They perfectly align with each other. Is that okay? The crest of one aligns with the trough of the other. So how happens? Then a flat wave. If there's flatness, so no wave is created. The wave is killed. Is that okay now?
Yes, sir.
All right. Okay. Okay, now there are two conditions too. There's something that we talked about. Do you remember when we talked about a string that is attached to one other end, and for the first string is free to move here? For this first string is free to move. The other string is fixed to the two ends. What will happen if I send a wave here? What will happen when it gets here? If I send a trough here, when I do like this, the trough will go here, right? When it gets to a free end, you have a free end and a fixed end. When it gets to a free end, what will happen? Will it send back? It will send it back. I can't stop now. To send it back. To send back the wave now. If I
Free end.
yes, for a free end, to send it back. Both of them will even send it back. But the question is, how will they send it back? If this one goes like this, will it send the wave back as a trough too, or will send it back as the same crest? If I send a wave, a trough, through the free end rope, as a trough, are you sure? If I do this, it comes here, this wave will no, it will send back as a trough too. If for a fixed end, if I send a trough should send it back as a trough should be sent back as a, if it's fixed. As a trough. Are you sure? If I send wave. Okay, so a wave that is sent as a trough on a free guy will not undergo inversion. Is that okay? So what will happen? To send it back as trough. Does that make sense? So to send it as trough, it sends it back as trough. Yes. It's just like when two of you are actually doing the thing. Do you get it? If you do it like this, the other person will do it back. Kind of. Do you remember? So the person will send it back as the same guy. So, but a fixed end will undergo inversion. If it's coming as trough, if it goes here as trough, it will come back here as crest. Is that okay? So there will be inversion. I'll keep looking at you until you can know. Then here there will be no inversion. Do we understand? All right. What's the next thing to be discussed here? Have we discussed polarization? All right, let's write plane polarization. Now, what is plane polarization? Plane polarization is just what? Is only now this one is only characteristic of what? Of who? Of transverse waves. Is that okay? So we call it plane polarization, or just polarization for short. Is that okay? Polarization is this. Now, we know already that let's try to draw two axes, three axes, the 3D axis now. Watch. So there is one like this. Let's put it here. So this is like, this thing is pointing out of the board. Is that okay? Let's put it this way. Does this make sense? It's pointing out of the board in that direction, in this direction. Okay? So for our typical wave, so if all of them extend out, this one will extend out like this, this one will extend to that back. Does that make sense? Are you seeing it in 3D now? God bless you. You are seeing it in 3D. That's good. That's how to see in 3D. When I draw it like this. Okay, let's go. So we have Y, X plane, Z plane. Now, see this. We know that light wave, for example, or electromagnetic wave, they travel in two directions. This direction, one. And the second direction is this. And this is not perfect. Let's draw a very nice one so it will make sense. Is that okay? So we can see it well. So we have something like this. Now then see the other one. The other one, so this axis, this wave now is between which axis? Y axis and what? X axis. Does that make sense? But look at this other wave now. So I send something like this now. Look at this wave. This wave is between Z axis. Does this make sense? Z axis and which axis? And Y. No, this one. This wave here, this new wave I just created here. It's between Z and X. It doesn't look like Y is involved at all. It's Z and X, but I can't even trace the X now. Okay, we can trace the X because, okay, yes, because it's going on this plane, it is X. Does that make sense? This is a particular y-axis, for this one. Okay, maybe I didn't draw it perfectly, but anyways. So this one will go like this. Okay. It should follow this. You get what I'm trying to draw, right? So this plane, there are two planes here. Does that make sense? One is like this, the other is like this. So one wave is going up and down, up and down. The other wave is going into the board, out of the board. Does that make sense? So what we want to do, what we want to achieve here is that I want to make this wave to travel in one direction. So what do? We'll polarize it by using what we call a Polaroid. Is that okay? A Polaroid can be made of different materials. I think we talked about Mica. Was it Mica? Is it Mica? Tourmaline. We talked about these two. Quartz, guys. Is that okay? Like glass, like guys. Is that okay? Like quartz. Okay. So now, this is the shape of a Polaroid. So for a vertical Polaroid, what will happen? Which way will pass through this slit? Is it the XY axis wave or the ZX axis wave? Will pass through here, right? The YX guy. Why? Because this guy is on Y axis. Is that okay? So it's only the YX axis wave that will pass through here. What will happen is that the ZX guy will be absorbed by these sides. It will not pass through. Is that okay? So at the back of this thing, what you now see is like this. Does that make sense? The second one would have been absorbed. Then if I wanted that one, Z and X, to pass, I can slant this thing like this. So which ones will pass now? The one that is going like this, right, will now pass through. The ones that are going up and down will be absorbed here and here. Do we understand now?
Yes, sir.
So that's plane polarization of light. So which wave cannot be polarized? Huh?
Longitudinal.
Longitudinal waves generally. Okay, so let's go to the next thing. So I think that's all on wave. Is there any other thing we have to discuss? Eh? Okay, we'll now do some calculations. But before we do calculations, I said we should consider light waves too. The light wave is long, so we'll do everything together. Is that okay? We'll do mirrors and lenses all together. Okay, now it is long, right? Okay, so let's go now. Light waves. Somebody say light waves. Show me the light. Oh, which one is that? Let there be light. Okay. So let's go now. Light waves. Now, basically, we say light waves is an electromagnetic wave, right?
Yes.
And it exists between the. We're supposed to do electromagnetic wave immediately. Now, how is light produced? Let me tell you how it is produced. Now, we said it's produced when first is one of the is in the electromagnetic wave spectrum, right? What is the electromagnetic wave spectrum? We'll talk about it here. Revox G, right? Revox G. What does R stand for? R. Radio wave. Infrared. Visible light. Ultraviolet. X-ray. Gamma ray. Now, this order is the order of what? This is the order of increasing frequency, yes. This is the order of decreasing frequency. If frequency is increasing here, what is decreasing? Wavelength is decreasing. But in this order, what is increasing here? Wavelength. Does that make sense? This is the order of increasing wavelength, increasing frequency, decreasing wavelength, decreasing frequency. Does that make sense? So it means that radio wave will have a higher frequency than a higher frequency, a higher wavelength than gamma ray. Is it clear? But a lower frequency than gamma ray. And let's go. So now let me explain something to you. Okay, now, so this band, the visible lights, that's what I want to discuss, occur in this V spectrum. Is that okay? The V spectrum is between what? 400 nanometers and what? And 700 nanometers. Is that okay? Or 4 times 10 to the power minus 7 meters and 7 times 10 to the power minus 7 meters. Does this make sense? Okay. I mean, nano means times 10 to the power minus 9. Good. Good. So what this means is this. This is the spectrum of wavelength. Now, this visible light is now split into what? Roy beef. Okay, you know what? Should we discuss this when we get to electromagnetic waves? I'll discuss in electromagnetic waves so you understand how light is actually produced. Let's talk about light generally first. Is that okay? So that we will not have to, since we are still going to do calculation. Now, electromagnetic wave, we said, is light wave. Now, light travel in small packets called what? Photons. Now, this energy or these packets are called energy packets, according to this guy, Albert Einstein. Is that okay? But I told you in particulate modern physics that Albert Einstein did not actually use the term photon, right?
Yes.
What did I say use? Use quanta. Do you remember? All right. So, but anyways, now we know there are photons. Those are the small packets in which a light travels. Small packets. Is that okay? So this is light, and that is what that's the essential, the particulate nature of light. Is that okay? Right. So we know that there are substances that can behave as both a wave and both what? Both a wave and what? A particle. Is that okay? Yes, so such as light. Light can behave as what? A wave and what? A particle. So now, those photons take a path to reach us or to reach anything. So that path that it takes is called what? Ray. Now, an aggregation of rays together, when many rays come together, what do they form? When we have plenty rays, what do they form? They form a beam. And there are two types of beam. So this, if this was a ray, then this would be a beam, right? Plenty rays together. Now if I have my beams to be like this, what kind of beam would we call them? Divergent beam. Is that okay? Or divergent beam? No, divergent beam, not divergent beam. Yeah, of course it's divergent. So we'll call it divergent beam. Then if I had my beam to focus at a point, what would that be called? Convergent beam, okay? Now, substances in the universe are classified into three based on their interaction with light, or what they do to light, or the effect that they have on light. Some are called opaque, the others are called translucent, while others are called transparent. Okay, before we even talk about this, we're supposed to talk about how substances produce light. There are two types of light, or light sources. Is that okay? We have the artificial natural light sources and what? Artificial light sources. Is that okay? So for example, one of the natural light sources is what? The sun, God bless you, and bioluminescent substances, right? Such as, is moon bioluminescent? No. Moon does not have light of its own. Where does it get light? From the sun. Do you understand now? Okay. Artificial guys now. We have what? Touch. How about incandescence? Did I mention incandescence? What are incandescent substances? They glow when what? When they are heated. Good. So we didn't classify as natural or artificial? Natural. Yes, when they heat them with fire that they glow. Okay, they can't glow without fire, right? Yeah. But they emit light on their own now. Unlike bulb. Bulb does not emit light on its own, except to pass electricity through it. Okay. Incandescent substances. They need to be heated. Okay. I guess they will be natural, produce light on their own. I guess it will be artificial then. Does that make sense? It means they need a surge to produce light, something to cause them to produce light, right? Okay. Are you with me? Okay, so now, translucent substances now. Opaque substances. Now for opaque substances, these are substances that what? That do not allow light to be transmitted through them. And there are three effects that you can have on light. Is either it is what? Transmission, right? Absorbance, right? Or what again? Or reflection, God bless you. Is that okay? Or absorption. Thank you. Absorbance or absorption is the same. Absorption. We use absorbance for liquid materials, actually, or absorptivity. Is that okay? Right now, or reflectivity here too. Now, what's transmission? Transmission is when a ray of light touches something. That substance contains some atoms that will vibrate in a particular way, and will transfer that vibration throughout his body and to the other end. So the amount of light entering them is the amount of light going out through them in a perfect condition. That will be for what? Transparent objects or substances. So an example is glass. Is that okay? Okay. Yes. A transparent substance is one that transmits the total light that enters it. So what is the transmission? How is the transmission happening? The ray of light will come at a particular frequency and vibrate the atoms of that thing. And as it vibrates the atoms will pass it to the next atom and to the next atom until they pass it through the other end. That's why if there's a window, there's a glass here. In this glass, there is light perfectly coming through the sun. Do you understand? is not dimmed. Does that make sense? I didn't know I put his clothes now, this blue shirt. I used it to cover this window instead of the glass. What will happen? Some amount of light will not get here, and in fact, it's because of the intensity of light, the light will actually still get here. Is that okay? Because his cloth is opaque or translucent, depending on the material too. Is that okay? Translucent substances are the one that they absorb some of the frequency of light and reflect the others. Reflect some. Does that make sense? Okay, so if they absorb some, they reflect some. Is that okay? And transmit some. Those are translucent substances. So transmission is with transparent and translucent substances. Is that okay? Example is tissue paper or even paper itself. You know, if you want light in paper, it might absorb some, but it will still allow some light to pass, right? Yeah. So that's a translucent substance. Right? Then opaque substances are the one that totally they are against transmission. Do you understand now? They are totally against transmission. What they do to light is what? They absorb and reflect. So that's what creates colors, right? When we get to electromagnetic, we'll talk about it now. Example of opaque: the wall, the chair, the table, this, everything you see around you. Even your trouser is opaque. That's why it's black anyways. Black substances, they absorb all and reflect none. White substances,
Reflect all and affect
none. So those two, we said they are not colors, right? Do you remember? Okay, now, so that is light wave. That is the simple characteristics of light. But those are the simple characteristics of light that I've discussed. Now let's talk about the laws. I mean, things that are associated with it, or the characteristics. The reflection of light now. Let's talk about reflection of light. Now, reflection of light, when light ray is incident on a plane surface, what happens? It's reflected on the other end. Now, if it's reflected on the other end, the angle of incidence also, according to law of reflection, will be equal to what? The angle of reflection. Does that make sense? Okay. Now, we also know that light travels in a straight line. Light does what?
travels in a straight line.
Yeah, and it's called the rectilinear propagation of light. Rectilinear propagation of light. And this phenomenon is provable in two major ways. One of the ways is the creation of shadows, and the second one is eclipse. Now, for shadows, when rays of light hit an obstacle that it cannot penetrate, what will happen? It will cast the shadow of that obstacle on the floor. Does that make sense? Okay. So, then eclipse, and there are two types of shadow we talked about here, right?
Yes, sir.
What are the two? Umbra and penumbra. Then for the eclipse is basically the same thing, but a special form of shadow thing. Now, it's when heavenly bodies cast shadow on each other. Yes. So heavenly bodies, like, what are the three heavenly bodies that are engaged in eclipse? Moon, Earth, and Sun. So now, what eclipsing means covering up. When we did modes of conformational analysis in chemistry, do you not do eclipse conformation?
Yes, sir.
So now, eclipse covering. Is that okay? There are three types of eclipse. We have eclipse of the sun or solar eclipse. We have eclipse of the moon or lunar eclipse. And we have eclipse of the annular eclipse. Thank you. Okay. Now, you see the eclipse of the sun is what? S-M-E. Eclipse of the moon. S-E-M. How are you? Let's do that. SME, that is, the moon comes between the sun and the earth. So the moon is relatively small. It comes between where? The sun, which is big, and the earth. Do you understand? So because of that, shadow is cast on what? on the earth. Do you understand? The shadow of the moon is cast on the earth. All right. But not entirely. When you see some diagrams, you see some portions that are deeply dark or deeply shaded. Those portions are the portions of umbra of the moon. Is that okay? Then there are portions that you see will be lightly shaded. Those are the penumbras. Is that okay? Those portions will be darkened, but not as dark as they experience darkness, but not as dark as the portions here. Is that okay? So then the lunar eclipse or the moon eclipse is when the earth comes between the sun and the moon so that the moon does not receive light at all. Is that okay? So just rearrange it. Earth comes here, moon goes there. Okay, then the annular eclipse is this. It's still like SME. Is that okay? But in annular eclipse, we say that the earth is at its perihelion. Do you remember? At its perihelion, peri, that is edge, helion. What does helion mean? I don't know. But the thing is, perihelion is when the sun is closest to the earth. Is that okay? The earth is at perihelion when the earth is closest to the sun, and the moon is at its farthest point from the earth. Is that okay? The moon is at its farthest point. So basically, what happens is that what you see is why it's called an annulus is from the word why it's called annular is from the word annulus. Annulus means ring shape. So I told you about this annulus. Okay, so what you see is the ring shape of the sun. So what you see is if there's the moon is still in between the earth and the sun, you now see a ring shape of light. This place will be basically illuminated, but the point is this moon is covering some parts of the air, of the moon, of the sun, so that and that's when the sun is closest to the earth and the moon is farthest from the earth. Is that okay? So any question you see that has to do with annulus or ring is what? Annular eclipse. Okay, so those are what the proofs that light travels in what? In a straight line. All right. In a straight line does not necessarily mean straight, it could be an angle. You saw what I drew there, right? So what's the next thing that we'll talk about? Let's talk about we talked about reflection of light. Now let's talk about mirrors then. Let's talk about mirrors. Right? Is that the next thing? Let's talk about mirrors. Now in mirrors, what's a mirror? The mirror is a substance that is a glass basically that is coated on one side. One side of it is coated. Just came. So one side is coated like this. And there are two types of mirror. We have the plain mirror and the curved mirrors. We have the plain and curved. There are two types of curved, right? The spherical, and what? Parabolic. Remember we said parabolic mirrors are those that can produce what? Parallel beam of light. Do you remember? Parabolic mirrors produce parallel beam of light, such as we see in headlamps of cars. And you see the headlamps of cars, they are something like this. And the bulb will now be here. You remember? So that to produce what? Straight beams or parallel beams of light. Is that clear? So parabolic mirrors are the ones that are very curved. Is that okay? And spherical, they are just fairly curved. So let's first talk about the plane mirrors. Now, when a ray of light is incident on a plane mirror, to reflected back, is that okay? And we also have what's called polished surfaces. So polished surfaces too have the capacity to reflect light. Okay, now this is my point. So for a plane mirror, let's talk about the images formed on a plane mirror. So for example, we'll be talking about a plane mirror now. If an object is placed in front of a plane mirror like this, let's say this person is observing himself in the mirror. Now, what are the characteristics of the image that will be formed? What are the things that is going to see? He's going to see an image of himself, right? That will look exactly like him, right? Okay. And to be formed on the other side of the mirror. This other side of the mirror is called the back of the mirror. So the mirror has a front and it has a back. So any image that is formed at the back of the mirror will be called what? Will be called what? Virtual. So, and we know that if an image is virtual, it means it cannot be, what does it mean? It cannot be formed on a photographic plate, right? Okay. Then we have, it is standing like the person is standing, right? So it is what? Erect. Does that make sense? It is erect. The image distance, is it real? It is not real. It is virtual, is the opposite of real now. So I told you to cram virtual and erect. They always go together. Do you remember? And real and inverted always go together. Okay, yeah, we even formed one thing like that. So the image distance, object distance is u. Image distance is what? V. So the V and the U are always equal. Is that okay? Then the other thing about it, it is laterally inverted. Laterally inverted. So right hand here, if you raise up his right hand, what will he be seeing? If you raise your right hand in the mirror, what do you see? In the mirror. If you raise your right hand up, and that's the mirror, what will I be seeing? It will look like the person raised the left hand. That phenomenon is called what? So lateral inversion is that thing, 180-degree flipping. Do you get it? So that's the case. Okay, so another thing about the image is that the heights are equal. Image or object height is called h sub o, and this one is h sub I. That is image height. The heights are the same, not one is taller than the other. Is that okay? All right. The moment your own mirror at home does not have this property, you know that your mirror is not a plain mirror. Okay. Yeah, well. So now what about curved mirrors? Curved mirrors. So remember this. We'll now analyze the images formed on these mirrors based on all of these properties. Is it virtual? If it's virtual, it will be erect. Is it real? If it's real, it will be what? Inverted. Okay. Now, for curved mirrors, there are two types of curved mirrors, right? No, before we talk about curved mirrors, let's still finish plane mirrors. Let's talk more about plane mirrors. Now, with plane mirrors, we could have two mirrors that are inclined at an angle. Is that okay? Is that okay? Inclination of mirrors. Inclination of mirrors. Now, if I put two mirrors together like this, if these two were to be a mirror, like this, and I put them like this, what angle is this? Angle 90 degrees, right? They are directly perpendicular to each other. So, with that, the number of images that will be formed, will be equal to number of images. Will be equal to what? Who can remind me? 360 minus 1. God bless you. So, what is that n? The angle is not 3 over n, 3 is over theta. So n will be equal to 360 over theta. Do you remember now? Minus 1. So that's the formula. Is it clear? So if I incline them at angle 90 degrees and I place my image, so this is one mirror here and this is another mirror here, perfectly at 90 degrees. I now place my object like this. Place my object more like, let me draw it in 3D so you understand it well. I place a mirror here and now place another mirror here like this. Are you seeing this? Now, and these are surface here. If I place my object here, a box here, how many images should I see? Let's see. At 90 degrees, probably at 90 degrees to each other. Theta equal to 90 granite, right? So number of images I should choose what? 360 over 90 minus 1. That what? Here for 4 minus 1 is what? 3. So I should see 3 images, right? And what will be the 3 images? This will be the object, One will be formed here, right? How would the other be formed? The other will be formed here, right? Okay, if you look at once, you will see, depending on where you are facing, I think you will see the one that is formed by this one at the back of this one. Do you get it? So, but don't count this one is object. Okay. Alright, so the angle depends or determines rather the number of images that you will see. Do you understand now? Okay, so that's that. What if I rotated the mirror? Okay, then there's another thing about inclination of mirrors. If I incline two mirrors like this, are you man? And I send a ray of light like this. This ray of light we touch here will be reflected, right? So we analyze this as angle of incidence, angle of reflection. This one will be the incident for this mirror, right? It's reflected in the same direction, right? Parallel to that guy. So we'll have something like this. That's what? This will now be the new incident. So I2, this will be the what? R2, second reflection. Does that make sense? So if this was angle 30 degrees, what is the angle between the angle of reflection and mirror 2? This is mirror 2, this is mirror 1. The mirror 1 is the first mirror that received the light. Is that okay? So if it were this one, it would be mirror 1. So the angle of, if I say what's the angle between the horizontal, the mirror, and the angle of reflection? Or angle of second reflection, what would that be? If this was 30, what would this be? 30. Why? Because I granite is always equal to R granite. Then what will I2 be? 60, because using alternate angles, this will be 30, then this must be what? 60, one must be 90, then here also what? 60. So what will be the angle? 30 granite. This is where you are being asked for in that question I just asked. Is that okay? The angle between the mirror and the reflected ray. If you don't understand what I just explained, raise your hand. You weren't listening. Okay, so rewind it. You'll get it. Is that okay? All right. So let's go to rotation of mirrors. How about rotation of mirrors? So what if I rotated mirrors? So for example, if I have a mirror like this, if I have my mirror like this, and this time my mirror is like this now. So here's my mirror, and I rotate it like this. Are you with me? If I rotate it like this, so I can rotate my mirror like this, rotate it back like this. You get it? So once I rotate my mirror, the angle of incidence, if I rotate my angle of incidence by theta, my angle of reflection will be rotated by what? 2 theta. Do you remember I proved this for you? Do you remember that I proved it? Oh. Do you remember I was arguing about something? Okay, let's go. So I proved it for you anyways. But just remember that if I rotate angle of incidence by theta, angle of reflection will be rotated by 2 theta. Okay, let's go to the next one. So we're done with mirrors, basically, plane mirrors. Now let's talk about curved mirrors. So there are 2 types of curved mirrors. There are 2 types, not 2 classes. We have parabolic and curved and spherical. So 2 types of spherical mirrors. That's what I'm going to say. Spherical, right? So 2 types of spherical. What are they? Concave and convex. Uti, what's another name for convex mirror? Diverging. Is that correct? What's another name for concave mirror? Converging. What does converging mean? Brings it together, right? So if I have my curve like this, if I shade the back, what kind of mirror have I made? A diverging mirror. Do you understand now? If I made my this and shaded here, what kind of mirror have I made? So any direction I put it, because some people are thinking that if I want to draw convex, I should always do it like this, then shade this place. Even if I do it like this, as far as it's the back here that I shade, what have I made? Concave all the time. Does that make sense? All right. If I shade the bulging part, that will be concave. So let's talk about concave now. What are images? Images formed on a concave mirror. Now, on a concave mirror, what are the terms we use in describing the concave mirror? Now, yes, we're going to talk about them. So this line here that passes through the center of the distance is called what? The principal axis. This line is called the principal axis. I'm going to take it in one shot. I will not draw anything. Is that okay? This point here, the middle of the center of the mirror is called what? The pole. Is that okay? Now, the distance away from the front of the mirror, which stands as the radius that produces that curve, is what? Or radius of the sphere that produces the curve, is the center of curvature. So we put it here, center of curvature. The midpoint of the distance, the midpoint of the center of curvature and the pole is called what? The focus. So around here, yeah? So this is the front of the mirror, this is the back of our mirror. Okay? So now, I'm talking about the images formed on the mirror. When you draw a ray of light to pass through, to be parallel to this principal axis, how will it be reflected? So if it's incident parallel, it will be reflected through focus. Okay? So if I have this, like this, it's reflected through here. Does that make sense? If a ray of light is coming through the focus, how will it be reflected? Parallel to the principal axis. If one comes from the center of curvature, how will it go? On reflected, yes. Because we said at every point, any ray that's coming from the center of curvature always hits the tangent to the curve on that point. Is that okay? So for example, you see this one too. This ray, this line is passing through the center of curvature, right? So it's coming back the same direction. We're going like this, comes like this, goes like this, comes like this, goes like this, comes like this. All right. Then the last one we use the last rule that exists that we don't normally use is if it passes through the pole like this, it's reflected at the same angle. But we cannot do that perfectly, so we don't normally use it. Is that okay? Theta is equal to theta. Does that make sense now? All right. Now, what do these guys produce? So let's talk about it. Now, we have our positions and the x-axis. Now, what are the positions we can put our object on this thing? Number one, we can place it at anywhere beyond C. Even here is beyond C. Even that place is beyond C, right? It's not beyond C, beyond C. Do you remember now? We can place it again at, that's the second position. What's the third position? Between C and F. What's the next position? At F. What's the next position? Between F and P. F and P, thank you. So there are 5 positions here, 1, 2, 3, 4, 5, yeah? So now, if I place my object at beyond C, what kind of image will I form? I will form a real image, inverted and what? Diminished. Real, inverted and diminished. And we've proved that, right? Okay, I'm going to leave a video in the description that discusses this in full. At C, what will happen? Real, inverted, same size as object. Same size as object. If I place between C and F, what will happen? I place at F, what will happen? If I place between F and P, God bless you. So it means that we have, once you master these positions, and this position is just as we go here. Is that okay? As we come towards the mirror. Beyond C, at C, between C and F, F, between F and P. What about P? Okay, so what do we have? We have read, them. All right, is that clear? River. Everybody go. One more time, you say. Abiodun, you're not talking. Okay, just wait for where we are. Let's go. I love you people. I love you people. We'll make another song now. Wait, is it even playing? Oh, okay. Let's go. So what's the next thing after this? We should learn of the calculations, right?
Yes, sir.
Before we do calculation, let's do refraction. Somebody say refraction. You say.
Right.
So what do we see in mirrors? We see reflection. What do we see in mirrors? Where do we see refraction? Lenses. What do we see in lenses? Refraction. Okay, so we have to talk about refraction now, right? You know, here we have to talk about many things. We'll soon start calculation. Is that okay? We'll do all the calculations from wave down to this point. Is that okay? So we are stopping at refraction of light now. That's the last part there. Okay? So what's refraction? Yes, we're doing lens. Refraction is under lens is under refraction. Is that okay? So now refraction is when what? The ray of light passes through from one medium to the other and becomes what? Deviated, right? So it deviates or it changes direction, as we rightly said the other time. So because of two media have different optical densities. So as it's coming from here, it's going to be reflected either in this direction or it's coming from this top. These are normal, is that okay? So it's going to be incident here and be refracted like this. Now, which of these is this light going from optically dense to optically less dense? In which of these diagrams, set of A and set of B, in which of these is the guy going from optically dense to optically less dense? B, optically dense, optically less dense. B. If it's going from optically dense, the speed will be less. If it's going to optically less dense, the speed will be more. So the answer is A. Optically dense means that it doesn't allow, like it impedes the speed of light. Do you understand? It means it's dense. Optically dense means it impedes the speed of light in a way. Is that okay? It reduces the speed of light. So the speed of light is more here. It's more here than it is here. That's why it's deviating away like this. So here in this case, angle of refraction will be greater than angle of incidence. Are we clear now? Is this still confusing? So this is optically dense to optically less dense. That is from optically less dense, e.g. air, right? To optically dense, e.g. water or glass. Do you understand now? Okay. Yes. CIR. What is CIR? Okay, totally. We'll soon get there. Okay, so now let's talk about, now, this is what happens. Depending on the kind of reflection that takes place, and depending on the media that you're using now, if I'm going from optically dense to optically less dense, you see that as I'm increasing my angle of incidence, listen now, as I'm increasing my angle of incidence, what will be happening to the angle of refraction? To be increasing, right? So if I increase this to something like this, I should get something around here, right? If I increase this to something like this, I should get something around that is exactly on the interface. Does that make sense? So it means that our angle of refraction has become what, 90 granite. Does that make sense? So that angle of incidence that creates a refraction of 90 degrees, or that makes refraction to be at the interface, exactly at the interface, is called what? critical angle. It's called what? Is the angle of incidence that makes this angle of reflection be equal to 90 degrees. Is that okay? It means that beyond, if I go a little beyond this, I increase my angle of this thing to this place. What will happen to this thing? It will come out. Is that okay? So this condition is called what? Total internal reflection. Does that make sense? Okay. So it means that the angle that produces total internal reflection is greater than the angle that produces what? Critical angle. So with this, let's define the law of refraction. There are two laws of refraction, and the first one is just like the law of reflection that says that both the angle of incidence and the refracting angle, they lie on the same plane. But the second one is called the Snell's law, and it says that the ratio of the sine of angle of incidence is to the ratio of the sine of angle to that of the sine of angle of refraction is a constant for any given pair of medium. So for example, if I have A sub W, it's going to produce a particular ratio that is constant for every time we have A sub W. Do you understand like that? Do you understand that way? That is what that law says. So for a condition of optically dense to optically less dense, we have our angle of our this is called the refractive index. It's called what? The refractive index for this kind of guy here is giving us 1 over sine C. Does that make sense now? For a condition where it is going from optically dense to optically less dense. Is that okay? Where C is the what? The critical angle. Is that okay? Are we clear? All right. So that's that on that. Now, what are the effects of? Now, what are the things that this guy can do of refraction? Yeah, what are the effects of this total internal reflection? The physical, real life effects of total internal reflection. What did we just say? Optically dense to optically less dense. If it's going from optically dense to optically less dense, that's when optically less dense means that it permeates light well, right? It permits light to travel fast, right? The speed of light is why another formula for refractive index is velocity of light in medium 1 over velocity of light in medium 2. Is that okay? Because speed of light reduces a little, very little though, when light travels from one medium to another. Is that okay? All right. So I now said that the total internal reflection, you said, okay, total internal reflection now. Now, what some of the effects, some of the physical effects? Because it's what? Mirage, right? Now, what is mirage? Mirage is when light is traveling from optically dense to optically less dense. Okay. When the atmosphere is in a cold atmosphere and a hot atmosphere, which one has higher optical density? Between a cold atmosphere and a hot or warm atmosphere? Optically, which one is more optically dense? Cold or hot? More optically dense. Denser. That is optically denser. The cold atmosphere is more optically dense than the hot atmosphere. Let me tell you what mirage is. Whenever you are traveling, if you have looked forward on a hot sunny afternoon, you will see like a pool of water is ahead, right? When you now get there, will there be water? No, right? The reason is because there is a layer of air in this atmosphere that is very close to the ground that you are. Is that okay? Let's say this car here. So you are looking ahead, and so because of that, I don't know why you're looking ahead though. When you're not the driver. So what should you be doing, right? You pressing phone, right? I don't know. Some people know what they usually do. What did you say? Go to war. Yeah, war against. This is a car. Look, are you with me? So when you are looking ahead here, you see a pool of water here. Reason is this: the layer of gas above here, and the layer of gas above the guy here is a little colder. Okay, let's choose around here because it has to be with respect to the angle from the car. Is that okay? So I don't want to choose somewhere very high. So if the layer of gas here, there's a layer of air here, and there's a layer of air directly overlying this surface. Is that okay? Are you with me? So the interface between them is just this thin line. So this one is this. Now which air will be colder? Which air will be hotter? Which air will be colder? A or B? Which one will be hot? B will be hot, right? Because in the afternoon, asphalt, black tar, is what? It's hot, isn't it? So the layer of air overlying it directly will be hot. So because of that, it will be optically less dense. Does that make sense now? Then the layer of gas above it, just above that layer of air, will be relatively cool. Does that make sense? Good. So what now happens is this: as ray of this thing is coming from the cloud, what makes up the cloud? Kind of like water, right? But it's gases, water, water and other gases, of course, but they appear like water too. Is that okay? So ray of light that is coming from the sky, now enters here, is now going to go from relative to your viewpoint, because a taller person, if you are standing, you see that you can't see, you won't see that thing. Is that okay? So the ray of light that is passing, that is touching this place, by the time it gets here, will be reflecting away from this surface. So because of that, you will now be seeing the image that this thing is bringing from the sky. That's what you will be seeing, and that is what, so that's what appears like water. Does that make sense to you? So ray of light that's come from the sun touches here. By the time it gets here, you are at an angle relative to that thing. You are seeing it at an angle that is greater than critical angle. Does that make sense? So because of that, total internal reflection will occur, and then you will be seeing the ray of light as the image that ray of light is bringing from the sun. Does that make sense now? All right. So that is for mirage. Now another physical phenomenon that we see with refraction is what? The rainbows, which is in dispersion, right? So dispersion of light. So what is dispersion? Now prismatic substances have a property of dispersion. They are able to scatter the rays of light. That's the dispersion of light, of polychromatic light. Is that okay? When we call it polychromatic, what does it mean? It means it's made up of many colors, right? So white light is made of many colors. We'll do that again in electromagnetic wave. But the point is this, that rainbow is formed because of, especially when rain just fell, that is when the rainbow comes out, right? So there are still suspended water particles in the atmosphere. So the ray, when you look at the sky, the ray of the sun that is coming from there so it's white light that's coming from the sun. So the white light will be segregated into the 7 colors reg beef. So that reg beef is what is now showing there. And it always arranges itself according to the spectra. Do you understand? It always arranges itself that way. Do we understand now? All right, let's go to questions. So before we go to questions, let's talk about we have not talked about lenses though. Okay, let's use lens to get to questions. So now in lenses, there are 2 types of lenses, right? No, that is through a color filter. Is there a color filter there? What was drawn? Come and draw it on the board. Please open in your phones. Open to that wave and all. And we said there are 2 types of lenses, right? We have the concave lens How's the concave lens like? This, right? What kind of lens is it? It's a diverging lens. Does that make sense? And we have the convex lens. Is it what? A converging lens. Does that make sense now? Convex, converging. Exactly. What would this one be called? What kind of lens is this? A plano convex, plane and convex. What would this one be called?
Convex meniscus.
Convex meniscus. Are you with me? This will be what? A plano concave. This one will be what? A concave meniscus. Okay? Concave meniscus. Okay, now let's talk about image formation on the lens. It's basically the same, but it's basically the same as what we had in that first one. But the difference now is that those rays, rim, whatever, are for what now? Convex lens. Is it clear at all? Okay, another thing is this. So we said it's for convex, all those guys, right? For convex lens. So we didn't talk about the use of concave mirror. So that's why we use concave mirrors. We use them for what? For shaving mirrors. Then we use convex mirrors for what? Side mirror of your cars. Is that okay? So we now said for a mirror like this now, for a lens rather like this, the center is called what? It's called what? The pole, right? Now, the radius of curvature here, we don't use center of curvature, we use radius of curvature, right? So we call it 2f. Is that okay? And here, f. Here we call it what? F prime and 2f prime. Is that okay? So that this will be the back. Is that okay? Do you understand? So where will your eyes be? Where will the observer's eye be? Here, good. The observer's eyes will be here because you're looking you're using your mirror to view the object that way. You understand? Do you understand? So you can see through it. So if a ray of light now, if you put an object here now, is that okay? It will be the same principle. When it's parallel to this thing, when it gets to the center here, what will happen? It will refract it towards focus. If you draw one that is passing through the focus, by the time it gets to the center of the mirror, it will refracted now, not reflected. Is that okay? This will be the incident ray, this will be the refracted ray. Do you understand now? So, and you can already see what I'm doing. You see, if this was perfect, it means to be producing an image that is what? In between f prime and 2f prime. Are you with me? Then, you're with me, right? Okay, so that's basically it. Then if you draw one to pass through 2f, you draw a ray to pass through 2f, it will be reflected, it will be refracted in what direction? The same direction, undeviated. Do you understand now? Okay, so that's that. Now, are you with me? I mean, of course, it's the same thing if it were here, and even our mirror was that large. You know what I'm saying? Okay, so it will be refracted along the same direction. So it will just go undeviated. Is that okay? To emerge undeviated. Now, are you with me now? For convex lens produces only what? What kind of business does it produce? Diminished, erect. Is it always erect? Yes. Diminished, erect, and at the back of the mirror. Is that okay? Diminished, erect, and virtual, right? Ved. Are you with me? Do you get it? All right. Okay, let's go to the other guy now. Let's go to calculations now. Let's go to what? Calculations. Now, we have concave mirrors and convex lens. So the convention is quite the same for both of them. So any object that you place in front of the mirror is always a real object. Is that okay? And it's going to be what? Positive. Anyone that is in front of the mirror. So image object distance. U is what? Object distance. And V is what? Image distance. Now, the image for convex mirrors, the image is always formed in front of the mirror. Concave mirrors, the image is always formed in front of the mirror, right? Isn't it? So image to be positive. Image is always positive for what? For concave mirror. Are you with me? Image is positive. But there is a condition for getting a negative image in concave. What's the condition? When the image is placed between F and P. Do you remember VEM? So VEM, a virtual image is always what? Negative. A real image is always what? Positive. Are you there? Now, if it's always erect, are you with me? And magnified. Is what? Magnified. Now, the mirror image, mirror formula or lens formula is given as 1 over F is equal to what? 1 over V plus 1 over U. Okay. As some people say is 1 over U plus 1 over V. Either ways, the magnification M is given by what? U over U. Now, if your convention is like this, use this formula. If your convention is like this, what do I say? But if you are using this convention now, look at my concave guy, I now draw an axis here. This is positive, this is negative, this is positive, this is negative. So that any guy that is on this side of the mirror is what? Negative. The height will be positive, but the distance will be negative. If my image is formed at the back of the mirror, the image will be what? Positive. The height will also be what? Even though it's at the back. This is the second convention. But I know it's this first convention, you know, right? If my guy now is now inverted, so it's what? Negative in height and negative in distance. Does that make sense? If it was formed here, that would what? Negative in height but positive in distance. Does that make sense? H sub I said represents what? Image, object, height. Object what? Alright, let's go on to solving some questions. And HI is what? Image, height. Okay, now, if you use this convention, your magnification will be given as minus V over U. And don't worry, any convention you use, you get the same answer. Are we ready to solve questions? Are you ready to solve questions? Are you tired? Are you tired? All right, let's clean the board. Give me your phone, or just open your phone. We have a question here. It says, the wavelength, before I attempt these questions, I want to call non-calculation questions. The first one says, it shows a diagram though. When you see a diagram like this, and you see wave going like this and like this, it says the wave is an incident and emergent. This wave incident, this one emergent. It has the wave phenomenon demonstrated in the diagram above is what? Good. So you don't need option here. Here, diffraction. Now, vibration in a stretched string cannot be polarized because they are dash. Vibration in a stretched string cannot be polarized because they are dash. A, stationary wave. Of course, they are stationary wave, right? B, transverse wave. C, longitudinal wave. D, mechanical wave. What's the answer? Longitudinal wave. The property that is propagated in a traveling wave is dash. Which property is propagated, in a traveling wave? A, frequency. B, amplitude. C, energy. D, wavelength. Energy, good. So we say it carries energy with it, right? By the way, the wave earthquake, what do you call it? Seismic wave, good. You know, like seismic earthquake, is that okay? The next one says transverse waves can be distinguished from longitudinal waves using the characteristic of dash. Transverse wave can be distinguished from longitudinal waves using the characteristic of what? A, diffraction. B, polarization. C, reflection. D, refraction. What's the answer? The right answer. Polarization. Good. Now we have 16. Number 16 says I, wavelength. I, medium of propagation. I, wave velocity. IV, frequency. V, energy. Should I write them down? We have the first one says wavelength. The second one, medium of propagation. The next one, wave velocity. The next one, frequency. The next one, energy. 1, 2, 3, 4, 5. So it says which of the above is used for characterizing waves? A says I, V. B says IV and V. I and IV and I and IV. Which ones do we use in characterizing wave? I and IV. This? Is that your answer? So you are saying wavelength, velocity, and frequency are the only ones we use for characterizing wave? Yes, that's the answer. Yeah, that's what we use for characterizing wave. Energy has to do with is in particulate nature of matter that we talked about energy. Do you remember Planck's constant? Energy that a particular photon brings, E equal to HF. We don't characterize wave by the energy it carries. Is that okay? At least not under this topic. Are you with me? Okay, let's calculate this fastest finger. If a light wave has a wavelength of 500 nanometer in the air, what is the frequency of the wave? C equal to 3 times 10 to the power minus 10 to the power 8. If a light wave has wavelength of 500 nanometers, 500 nm in the air, what is the frequency of the wave? Given that C is equal to 3 times 10 to the power 8. Why are you not solving? A wavelength of 500 nanometers in the air. What is the frequency of the wave? C. The options we have 3 times 10 to the power 14 hertz. B 6 times 10 to the power 14 hertz. C 6 times 10 to the power 12 x. 2.5 times 10 to the power 14 hertz. 14. Who agrees with him? Is it correct? 3 times 10 to the power 14? C, velocity of light is 3 times 10 to the power 8. What do you say? 6 times 10 to the power 14. So I guess that's the answer then. Alright, are we good? The phenomenon of the light traveling round an obstacle is what? The phenomenon of light traveling around an obstacle is what? A, reflection. B, polarization. C, refraction. D, diffraction. The answer is what? Diffraction. Whenever it talks about bending of light, is what? Diffraction. All right, let's go. The next one says, which of the following waves are both mechanical and transverse? It is mechanical and it is transverse. A, radio wave. B, sound wave. C, water wave. D, X-ray. X-ray. And that is water wave. Water wave is mechanical because it requires that water medium for propagation. Then it is also mechanical, and yeah, that's why it is mechanical. Then it is transverse because I use that example. If you drop something inside water, even if that thing doesn't float, doesn't sink, to first go up and down, up and down, up and down. Its own displacement is y, negative y, positive y. The water wave will spread x-axis. You understand? Is it clear?
Yes, sir.
The next one says, I guess that's all. Let's go to these calculations then. Should we start from this one? We start from number one. This one. V is equal to, what's this thing given? Frequency given, wavelength given, lambda. 500 nanometers, right? Given that V is equal to F lambda, it means that V is C in this case. I told you those are the two conventions. F lambda. And we're looking for the frequency, right? So frequency will be equal to what? C over lambda. Does this make sense? Okay, so frequency will be equal to what is C? 3 by 10 to the 8 over lambda is what? 500. Nano means what? Times 10 to the power minus 9. So you have this, that will be 3 over 500 times 10 to the power 8 minus 9. That will be 8 plus 9. This is one clear? Division means minus 9. That will be plus 9. So we now have 3 by 500. Or the best way would have been, let's remove this 2. That will be 3 over 5 times 10 raised to the power. Now, this will now be minus 2. Does that make sense? Plus this 17. Are you with me now? Okay. So 3 over 5, that's 0.6. So 0.6 times 10 raised to the power 15. You bring this guy to the front, you reduce by 1, right? 6 times 10 raised to the power 14 heads. Is it clear? Okay. So now let's go to these calculations on the board. Let's start from number 1. No. Don't worry, it's just this side I will use. Okay. The first one says, the equation of a wave, and we didn't talk about the equation of wave, right? Alright, everybody follow me. So for a wave, the maximum vertical displacement is given by what? A, everybody, A sin theta. So y equal to what? A omega t. Alright, if we introduce phase difference, we become what? Phi. Is that okay? That is considering 2 points, 2 segments on the wave. Let's say I'm continuing from here to H. Is that okay? Yes. So there's phase difference. Okay, so y equal to A sine omega t minus, what is phi? Do you remember that phi is 2 pi x? Okay, so we have 2 pi x over lambda. So y will equal to what? A sine, what is omega t? 2 pi f, God bless you. T minus 2 pi x over lambda. Recall that f is equal to what? V over lambda. You remember? So y equal to, this is our last step. A sine 2 pi v over lambda t minus 2 pi x over lambda. Okay, so we can take this out. Take this out. So we have y equal to a sine of 2 pi over lambda times v sub t minus x. So any form of all these equations, how many equations do we have? 1, 2, 3, 4, 5, 6, 7. Any form of these 7 equations will help us in solving all of those guys. Is that okay? Are you sure we're not cleaning anything here? I'm not sure this one will ever assist us, so let's clean from here upwards. If you don't know how to derive this equation, raise your hand. Going on to these questions, we have the equation of a wave traveling in a horizontal direction is expressed as y equal to 15 sine pi minus x. So which of these equations do you think will fit? The last one here? Okay, so we have, what is lambda? Okay, so we have y. So what you basically do is you want to compare. So bring up this equation is equal to, see, if you don't know how to derive this equation, at least master these last three. Or this one, this one. Is that okay? Master it. Tell your neighbor, master it. Okay. Don't put master in my it. 15 in this case, sine pi into bracket 60t minus x. Does this make sense? So compare to this guy. If we compare to this guy, it means that this place must be equal to this place. Does that make sense? This place must be equal to this place. Does that make sense? This place must be equal to this place. Does that make sense? All right. So let's compare. We are looking for lambda, right? So pi should be equal to 2 pi over lambda. Does that make sense? So that lambda will be equal to 2 pi over pi. Does this make sense? When you cross multiply. So pi cancels pi. So lambda equal to 2 meters or whatever unit you are giving. You can either be given centimeters or meters. Is that clear? So we're done with that. That's all. Number 3, we don't know yet. It says to find. Please help me look for that question.
No, 3.
Okay, so number 3 says find the progressive wave equation. Why is it? No, not find. Given. In answer, we should calculate lambda. So what do we do? Let's compare. So in this case, our pi is inside the bracket, right? So we'll come and use an equation where pi is inside the bracket. Pi is outside here, right? So we use this one. Does that make sense? Okay. So we write our equation y equal to 5 sine 2000 pi t minus 0.4 x. Does that make sense? Okay. So what is lambda now? Because I calculate for lambda, yeah? Okay. Somebody say okay. So where's lambda in this equation? So we can only compare to this, right? Where's lambda in this equation? This place. Does that make sense? So we can just bring minus 0.4x. The reason why I'm bringing minus is because it's not necessary. Minus always take care of minus, so you can just remove. So we say remove. Because this could be positive. If this were positive, you have to put minus. Is that okay? In an expression where that is the case. Equal to 2 pi x over lambda. X takes care of x. Does that make sense? So lambda will be equal to 2 pi over 0.4. Here 1, here 0.2. Lambda equal to pi over 0.2. Does this make sense? You take this guy here, this will be 10 pi. Does that make sense? You know this is 1 pi. That will be 5 pi. Do you agree with me? It's just simple maths. You know this is 1 times pi, right? Okay, 1 over 0.2 is what? 10 over 2. Does this make sense? Good. As you bring this, you move once to your front. Is that okay? You move once here, you move once at the top too. Here 1, here 5. So the answer is what? 5 pi. So lambda equal to what? 5 pi. Who's not clear? But was it the maths I did there? Is it the maths I did that confused you? The formula? How? We just used this place. We compared it with this place. They must be equal. Since this looks very much like this. If we're told to find frequency now, what are we going to do? We just say 2000 pi t will be equal to where? 2 pi ft. Who does not understand this? 2000 pi t, we compare with this guy. And we have this. Is that okay? 2 year 1, 2 year 1000. T year T, pi. F equal to what? 1000 hertz. Is it now clear? Is now clear, right? God bless you. Should we go to the next one? So what does that next one say we should do? This one, what does it say we should find? It's on this side. X over 30, pi over 34. Let me see. You just write it. Okay. 2 layers of wave separated by 17 centimeters. We have a phase difference of what? So phase difference occur here, right? What is phase difference? 2 pi x over lambda, right? That should be equal to pi x over 34. Does that make sense? But either way, there's nothing like phase difference here, right? So just say phase difference, therefore, should be equal to what? Pi x over 34. Does this make sense? So what is our x? The distance, horizontal distance is what? 17 centimeter. So now 180 times 17 over pi is 180. Everybody say pi is 180 over 34. Year 1, year 2, year 1, year 90. What's the answer? 90 granule. Somebody say 90 granule. 90 granule. If the phase difference is 45 granule, what is the value of x? Very simple here too. Everybody fast. I'll count 1 to 3. 1, 2, and number water. Is 1 the answer? Okay, someone has gotten 1. Fastest finger. Since yesterday. They're not waking up. 1, correct. This is all it. Good. Since yesterday, Tolu, you've not gotten an answer. Tolu Wani, you've not gotten an answer. What is it? Eh? Joy, you've not gotten an answer too.
I want to look at the page.
45 Jesus. 1, right? Are we good? Alright, so the answer is 1. How did you get it? Who can come boldly to the board to come and solve it? Head boy. DMB, come. Fast. A round of applause for DMB. For common 1, 2 question. Watch you listen to your teacher. Oh. Okay, please talk so that they can hear you. Okay, we'll go. Did you cut it? When? That means work. To be joining videos. Like you've cut twice now. I'll just dash it to go and do it. Give me my marker. All right. So is this correct? Okay. Let's go to the next one. Give me your phone, please. Okay, so this one now, let's solve it. I'm going to be reading a question. You tell me your answers in 2 seconds. Are we good? Are we good?
Yes, sir.
That was even fast. That was even slow rather. Okay, look at this now. This waveform, it says, use the waveform above to answer the following questions. Number one, which of the following distance is not equal to the wavelength of the wave? Which of the following distances is not equal to the wavelength of the wave? A, Cj, B, Bh, C, Dk, E, D, Ag, fastest finger. Dk, right? That's good. That's good. Because for it to be equal, it has to be, if it's from D, it should be end here, right? They must be in phase. So this side and this side, distance between lowest troughs. What do you call it? Two successive troughs. Okay, that's very good. The next one, which of the following pairs of points are not exactly in phase? They are not exactly in phase. A and G, B, C and E, D, B and H, D, G and M. They are not exactly in phase.
C and E.
C and E, correct. The phase difference between points A and J is dash. A 0 rad. In rads now, in pi. This is pi now. B pi over 2 rad. C pi rad. D 2 pi rad. The phase difference between A and J.
A and G.
Yes.
That's how it is.
It's not there, right? That's true. I don't know. Because
A and
Have you seen it?
J or A. That's true. What's the phase difference between A and J actually? Because from here is 2 pi plus pi. Yes now. Plus pi over 2. So what should I give you? 2 number 1, that's 5 over 2 pi, right? So the answer is not there, right? Okay, the next one. A second waveform having the same speed but twice the frequency of this waveform shown will have a wavelength equal to dash. The next, no, this same guy. The next question says, which is the last one. They say a second waveform having the same speed as this wave, but twice the frequency of the waveform shown will have a lambda equal to what? Now equal to what? He said equal to AM, CL, JN, and EJ. It's not so clear to me too, but it's not hard. It said a second waveform that has the same speed. So V is V, right? For both waves. But frequency, it says the frequency is now twice this one. So the frequency of this one is F. The frequency of this one what? 2F. It now says, what will be the wavelength? The wavelength will be equal to V over F, right? So in this case, 2 times this. So what will be the wavelength? Lambda here will be equal to half of the wavelength. Very simple nonsense. What's the answer? Some people did not listen. Some people are not listening. Did you get that? What I said? You weren't listening. Did the brother get what I said? What did you say? Okay, so now let's go again. It says a second waveform having the same speed but twice the frequency of the waveform shown. Twice the frequency. So if you ask twice the frequency, what will happen? So it's going to be, so the lambda of that second wave is going to be what? V over 2F, right? That is half whatever we had before, which was what we had here. So half the, so the wavelength is going to be half, right? So what is half? So what is half there? So which of these is half, right? AM is not half. CL is not half. A and E and J, let's see. Where is E? E and J, God bless you. Shop Noko. God bless you. Where are we, please? Where is he? All right. Are we good? The next one says, this is your phone. Number 6. And this thing looks like a camera. Yeah. Thank you. Okay, now this one, this number 6 now. It says, if the frequency of waveform A is 60 hertz, the period of waveform B is what? If the frequency of waveform A is 60 hertz, the period, did you get my question? If the frequency of waveform A is 60 hertz, the period of waveform B is what?
0.6.
A 0.025 seconds, B 0.25 seconds, C 40 seconds, D 60 seconds. Should I solve it? First, let me write the question. That if the frequency of waveform A is 60 hertz, the period of waveform B is what? You remember that frequency is equal to 1 over T. So this 60 is equal to 1 over a particular period. So T equal to what? 1 over 60. Does this make sense? What would that be? 0.0167. Let's do this way. Per seconds, right? No. Yeah, period is frequency is per seconds. Period is seconds. Does this make sense? This is the period of waveform A. So that is period of waveform A is the time taken to complete one. So this will be 0. Where's waveform A? Sorry, this, right? So the time taken, so this is one cycle in waveform A, right? So this will be 0.0167. So in this place, this will be half, right? So half of this will give us what? Just divide by 2. 0.008 3 what? 3.5. After 5 is what? So 3.5. Is that okay? So see what you now do. You now add it to this. That will be 0.0167. What would that become? The answer is 0.25. 0.025 rather. What's the answer there? This will be 2. The other one here, 5. Now that's 0.025 seconds. Option A. Do you understand me? If you don't understand what I did, raise your hand. You don't understand what I did? Who else doesn't understand what I did? Does the boy understand what I did? Come and explain to you, T. How do you understand? I cannot explain. The time taken to complete one oscillation, one cycle. So one cycle. So for waveform A, this is one cycle. So this is the period here. So waveform B now continues with one more loop. Does that make sense? So it continues with one more loop. So this one more loop here will now add to know its own period because this is waveform B. So we'll now add from here to here we take another half of this period, which is this 0.0835. By the time you now add it to this to give you the period for waveform B. Does that make sense? All right. So the next question. This question says, sit here. What does it say? Number 7, okay. Number 7 says that in the waveform shown in the figure above, energy is transferred from P to Q in 5 times 10 raised to the power minus 3 seconds. In 5 times 10 raised to the power minus 3 seconds. That's the time, right? Is this period? Is this time or period? Or time and period? Energy, hold on, ma. Yes, ma. Energy is transferred from P to Q in these seconds. So I'm asking this thing, is it time or period? Is there a difference between time and period?
Period and time.
I told you that there's a difference between time and period. Yes, period is the time taken per number of revolutions completed.
Yes.
Do you understand me? So there is difference. So this is time, not period. Is that okay? Did you get it? Everything between time and period.
The time is a complete.
See, look here. If I have from here to here, you go and watch that video. If this took 5 seconds, this is not the period of the wave. This is the time total. You understand now? The period of this wave is time taken to get to this place. Do you understand now? And how do you get the period now? Just check like this now. You have this gave you 5 seconds, right? So it means from here to here. It means you have 3 divisions of this. So just say 5/3. That will give you the period of this wave. Is it clear? Okay. So it now says the frequency of the wave is what? If it goes from here to here in these seconds, what's the period of this wave? So first check how many wavelengths do we have here? How many wavelengths do we have here?
2.5.
2.5, good. So 2 and 1, 2.5. Okay. So it's like just saying how many revolutions do we have here? 2.5 revs. Is that okay? So the period is going to be the time taken, which is time taken over number of revs. Does that make sense? So period is going to be time, which is 5 times 10 to the power minus 3 over how many revs? 2.5 or 2.5. Does that make sense now? So here 1, here 2. So the answer is 2 times 10 to the power 3 seconds. Minus 3 seconds. That's the period, right?
Yes.
2 times 10 to the power minus 3 seconds. But it says we should find the frequency. Is that okay? So frequency is equal to 1 over t. So this becomes 1 over 2 times 10 to the power minus 3. That will be 0.5 times 10 to the power. So that will be 5,000, right? No, 500 hertz. That's the answer. Is that okay? Times 1,000 here. You have a question? Okay. All right, let's go to the other aspect of this thing now. Of calculation. Give me your 8 what? Okay, question 8. A plane sound wave of frequency that and velocity that is reflected from a vertical wall. Can you attempt it? Or will you attempt it? You don't want to? Is it hard? So why don't you want to attempt it? Should we do it? A plane sound wave of frequency D's. F is what? 85.5 hertz. Look at where I'm solving it. And once you encounter a parameter, you write it. And velocity V's. V is 342 meters per second. Is reflected from a vertical wall. It now says, so the sound wave touches the wall and is reflected, right? Echo, yeah? So to produce echo. At what distance from the wall does the wave have an antinode? So wave is going, touches an obstacle. Once it strikes this obstacle, goes like this, right? So when does it have an antinode. Does that make sense? So the first thing we check is what is the wavelength. Now, do you understand now? If we get the wavelength, what's the wavelength? V over F. Are you clear on what I'm doing first?
Yes, sir.
Okay, because you remember when we were doing sound wave, we said you want to calculate the length of this thing and use it to calculate in wavelengths, right? Okay. So will you have an antinode? Oh, sorry. This is a node. This is an antinode. Thank you. This is a node. This is an antinode. So at what distance from the wall does the wave have an antinode? Okay. So first let's check the wavelength. What will be the wavelength? 342 over what? 85.5. What does it give you? 4. Okay. 4 naira. 4 meters, right? That's the wavelength. If that is the wavelength, a plane sound with that frequency is reflected from a vertical wall. Eh? At what distance is it? How did you get to? Divide by 2. At what distance from the wall? What are the options in the question? At what distance from the wall does the wave have an antinode? When will you encounter an antinode? So let's say at simple now is 1. At 1/4 of the journey now, 1/4 of the cycle.
Yes.
If the wavelength, are you with me? If the wavelength is 4, so 1/4 of this is the antinode. If you are coming from here, 1/4 is the antinode. So the answer is what? 1. 1 meter or 1 centimeter?
1 meter.
1 meter. Are we good?
Yes, sir.
Is it hard?
No, sir.
Okay, so you see, just thinking we did. You understand? All right. So let's go to the next set of questions. Following does not describe the image formed by a plane mirror. Who picked 4 and 7? You didn't check it, right? And we'll just talk about it then. And let me list the ones that are not calculated. Which of the following does not, that's 4. 7. Two mirrors of the same length are arranged as follows. 2 mirrors of the same length are arranged as follows. A ray of light NO strikes the system at O. So this is incident ray, right? And this is reflected ray. This is reflected 2. This is reflected 2, but incidence 2, right? Reflected 1, but incidence 2. Incidence 2, good. So the emergent ray has been deviated through what? Through how many degrees? Let me use it. You see, a value is not given us here. There's no value that is given to us here, right? But just use common sense. When 2 lines are parallel, what's the difference between them? 180 granite. You understand? See, this thing came from here. So it's more like the deviation is supposed to continue in this path, right? So it's now reflected like this. How many degrees is this? 180. No, I'm not talking about this line. I'm saying instead of being like this, that's turned and become like this. That's what? 180 degree. But let's prove it using using numbers. Is that okay? So if I have something like this, and it says that angle of incidence now 30 granite. Let's say it comes from here. Let's use here 30 granite here. Let's say it gives us this place at 30 granite. What will be the angle of incidence? Angle of incidence will be what? You just draw your normal radar. This is what? 60 granite. Then this is what? 60 granite. And this is what? 30 granite. Does that make sense? And this is what? 30 granite. Okay. So this thing that came from here was supposed to go like this, right? So what's the difference between this angle here, and this angle, this angle here. Eh? If you look at it, it's very this thing is more. You see? You see? Are you me now? This one we are calculating this to this, right? Okay. But you know it's 180 now, right? How did you prove it that day? If you use this line now, look at it. How do I even explain this now? It has been deviated. By how much? The deviation is the distance from here to here. This angle here, okay. This angle here, right? Okay. What's this place? 30, right? 30 plus, what's this place? 90, right? 30 plus 90, 120. Is that 120? This is the deviation. No, okay, sorry. This deviation is the angle between here and here, right? So I'm looking for this deviation. This angle here, this angle here, and this angle here. Are you with me now? Okay. If here is 30, this is supposed to be 60, right? Does that make sense? Please pause it so as to not waste our time. We said that the total angle here is what? 150, and that is the total angle here, 150. So this line here is 30 degrees away. So plus 30, that will be 180 degrees. So it's always 180 degrees. The next one, if the distance between the object and the pinhole camera is reduced. And I said we didn't talk about pinhole. For pinhole, if you want the image to be bright and sharp, I've talked about it before. What do? You reduce the distance between the hole and the back of the distance where the screen is, where the image is formed. If this is our pinhole, so this aperture here must be small. Is that okay? Must be small so that the image will be sharper. Is that okay? But to be inverted, right? So if you now reduce this distance here, this will be the object and image distance. Does that make sense? And this is the object distance. If this is our object now, here is object distance. What does it now say? It says if the distance between the object and the pinhole camera. So I now said if you increase the size of this aperture, this opening, what will happen to your image? It will be large and not sharp. It will not be sharp. It will not be constant. You understand? Unlike if there are many holes too, it will not be sharp. So there are two conditions for a blurry image. Number one, this wide aperture and plenty aperture, and fardance away from this guy produce blurry image. But a tinier aperture, less one hole, and closeness to this thing will produce sharp image. Okay, so now I have this. Now the distance between the object and the distance between here and here is u. So we reduce by half. So u1 will be what? U. Let's make u1 u. Is that okay? It's reduced by half, comma. Okay, by half the size of the image.
Okay, by half the size. Okay.
I think my question is wrong. Okay, by half the size. Okay. So if u was u initially, u2 now becomes half. Do you understand now? Half u. Does that make sense? The object distance is reduced by half the size, comma, the image of the object is now what? Is this doubled, is quadrupled, remains the same, or is halved? Let's try to use common sense. Let's try to use maths first. If u is this, so if u1 is u, then v1 will be what? V. Does that make sense? Then so what again? So what will v? Okay, we are now looking for v, right? The image of the object, v2. Does that make sense? Is now what? So magnification 1 of what? V over u. Magnification for this setup of what? For this setup. M2 now what? V, which is what we are looking for. Let's say V2 over u, which is now u over 2. So 2v over u. Does that make sense now? So if we take the ratio m1 over m2, m1. Okay, so m2 we go to v m2 we said would be v over u1, and u1 is what? 2v. U1 is u2 will be half of u, right? So u will be equal to 2. So if we substitute that into this place, that will become u over 2, which will give us this, right? So m2 is now 2v over u. Does this make sense? And we know that u from here is what? V over u. So this now becomes m2 equals 2v over u. What is u? V over m1. Does this make sense? So that this becomes m2 equals 2v over v times m1. So what happens to the multiplication? m2 becomes what? 2m1. Is it clear? It doubles. Yes? It's confusing. From where? Would have said what? God bless you, 2 times v over u. Because m1 is v over u. So we just say 2 times v over u. That is double. Is it clear?
Yes, sir.
See, that's sharper. Okay. Let's solve the next one. If an object is placed between two parallel plane mirrors with their reflecting surfaces facing each other, how many images of the object will be formed? They are reflecting surfaces to get to each other. Parallel to each other. If they are parallel to each other, what does that mean? 180 degrees. Theta equal to what? 180. So number of images is equal to 360 over theta over 180 minus 1. Here 1 here equal to what? 1. Right, the next one. An object is placed 3 centimeter high. An object 3 centimeter high. So height of object is what? 3 centimeters. It's placed vertically 10 centimeters in front of, so U is equal to 10 centimeter. U is object distance from, so that's the distance of that guy from the concave mirror. If this object produces image 40 centimeter high, the object produces image 40 centimeter high. So image of height of image 40 centimeters. Eh? From, thank you, that will be V, right? And the height of the image is what? H sub naught. H sub 1 will be what? Okay. So you know that magnification is equal to Hi over H naught and is also equal to V over U. But wait, I would have said we will be able to use common sense here. You know that, yes, it's quite possible. Calm down. If your guy, I think we knew the focal length now, would have been able to do it. But for it to be magnified, for the image distance to be far, the image distance for it to be far, it means that it is beyond, we have gotten, we are close to the mirror than beyond C. Do you know the meaning? Do you understand that? We are probably between C and F. Because at F, what will it produce? Infinity. So it means you are between C and F. If you are between C and F, then your image should be produced at a distance that is farther than the center of curvature. You see the way I analyze now? If we are given center of curvature or anything, we can easily pinpoint our guide here. Thank you. Let's do this. Hi will be equal to this times this divided by this. Does that make sense? So that will be H naught. That will be 3 times this times this. 40 divided by this. 10. What's the answer? 12 centimeters. The image and object distances, and you see, we're not supposed to solve. Do you know that? Right? Because we know the guy is 10 centimeters in front of the, so it means it will be between C and F. And C must be greater than 10. So it will be beyond C. So the answer, the greater one here is what? 12. Do we need to solve? Is it clear? Okay. This is very applicable in cases where you are not sure what to do. The reason is quite direct, right? The image and object distances of a converging mirror are related by this, and this is this one. Which graph represents the relationship between M and V? M is directly proportional to V. Does that make sense? So if it's directly proportional, which image is correct? This one. Can magnification be 0? If magnification is 0, what does that mean? When can magnification be 0? Magnification is not 0. Magnification cannot be 0. So what will be the answer? This. Is that okay? Because this one is the inverse. This one means magnification is negative. Magnification is not negative. So this one is inverse too. So the answer is A. Is that clear? Alright, let's go to the next part. Are you excited? Yes, sir. Oh, bless you. I love that response. Let's go. Okay, so let a boy that is excited. Let's go. Are you tired? Okay, so we have application of light waves. Application of light wave has to do with cameras, eyes. Okay, we are supposed to discuss cameras, also. The part of the camera and the eyes. Let's first talk about the eyes. I'll not say it. Telescope, projector. Let's discuss these two basically. These ones are very microscope too. Yes, thank you. Okay, so now with this, the eyes, we must know some a few parts. Is that okay? So how do you draw the eyes? What does it look like to you? Is that okay? So, maybe we should post. No, let's just label as we draw. So this first, okay, there is a layer here, right? There's a muscle here. Does that make sense? What do you call that muscle? Ciliary muscle. Ciliary muscle. Is it double L? No, one L. No, double L. I think it's double L. Anyways, ciliary muscle. Okay, one L, thank you. So then there is, this guy extends here. So we have our guy here. And we have one guy here. And one guy here. Something, there's a tissue here like that. That goes like this. And this is your eyes. So this guy extends here, like downward. You know, something like this. Are you with me now? What is this guy here? Okay, so this guy here, there's a guy here that I said. Okay, so what would this guy be? I'm coming on. So what would this guy be? Coming. So what will this guy be? So this guy is what? The lens. I mean, their names here, yeah? So what's this place called? Well, God bless you. No, this one is the vitreous humor. Is that okay?
Yeah.
Humor. And this one in front here is going to be the what? Aqueous humor, right? Okay. This one here, this space here, this space between these two. What's this? What are these two called? These rod-like guys. The iris, right? And the space between them is the what? The pupil. Does that make sense? Then this tissue that holds on to this guy. There's a tissue here and there's a tissue here. This one is called what? This guy is called what? The suspensory ligament. Then, of course, there's the cornea, right? There's the cornea. And of course, so there's this small part here is called what? The fovea, right? What's another for fovea? Yellow spot. Okay. And the portion where light does not fall is what? The blind spot. Then, of course, okay, so then the back here, the most light sensitive part, which is around here, this back here is what? It's going to be what? Retina. Retina comes like this from here. Do you understand? Retina. And retina is embedded with rods and cones, right? So the rods for light, right? Dim light. Cone for what? Bright light. Okay, so it means that cone is for bright light and the rods for what? Dim light. Okay. Then so now there's a question that I usually ask. The shutter of the camera. So the camera too has an aperture. Is that okay? So that aperture, what controls it now? What controls it? The lens, the guy too has a lens, right? an adjustable lens. So what helps to reduce the size of your lens or increase it or make it slimmer? What is that? The suspensory ligaments help in that work, help in holding it in place, but the iris is what actually does the work. So if the light is too much, this iris will come forward, kind of, is that okay, and make the lights to control the amount of light that enters into your eyes. Is that okay? So then, and of course, the iris is the part of the eye that is colored, right? Okay, so then so this, I'm supposed to know these things. Camera, all of this corresponds to what? This lens corresponds to lens. Now iris corresponds to what? What does iris correspond to? Is your technique here? Following are the differences between the eyes and the camera. So we have, the eye has a flexible lens. So the lens can become bigger or thinner, bigger or smaller. Is that big or small? Yeah, kind of. The thickness will reduce, okay, and then will slim out when it's stretched, right? So when this guy opens up fully, so we have that. So, but this one is a rigid lens. You cannot adjust that way. Is that okay? All right. Then the retina is equal to the what? The film in camera. The film. So pupil and aperture, iris and diaphragm. So how do we make our distance? So we have FRPI or F flipper. Does that make sense? Flipper or flip, flexible lens, F flexible lens, then retina. So flip will correspond to FRAD, R FAD. Do you get it now? Don't forget to flip, we scattered it. So to correspond to flip, RFD. Is there no way you can make sense of this thing? Dr. AF. God bless you. So that will be if PR, then Dr. AF. Does that make sense? If PR, then what? So if here is what? Iris corresponding to what? F corresponding to what? Film for? No. Rigid lens. Because here is retina, this is eye zone. Is that okay? So flexible lens, rigid lens. Pupil, aperture. Retina, film. Is that okay? If PR, Dr. A. Okay. Dr. A. Okay, now let's talk about the okay, now the human eye has what is called a far point and a near point. Is that okay? The far point is the farthest distance we can see, and the near point is the nearest we can see. Is that okay? Nearer than that, nearer than the near point, images appear blurry. Farther than the far points, images appear blurry or unseen. Is that okay? The human eye. So the human eye has a near point. Is that okay? Our near point is what? 25 centimeter. Do you remember? And our far point is what? Our far point is what? Infinity. If you put it, this is 25 centimeter, about 25 centimeter. If you put it closer than that, it will be blurry. Do you get it now?
Yes.
Because at that point, there's something called accommodation. Is that okay? Is that okay?
Yes.
And there's something called binocular vision. Now, accommodation is your ability to focus image, your retina to focus image on your lens. Is that okay? Of your eyes, rather, to focus image on your lens. Then binocular vision is your eye to superimpose image perfectly so that both eyes can see one image. Does that make sense? Now let's talk about the eye defects. Now what are the eye defects that we have? We have eye defects. What are they? Myopia. What is myopia? Short, because it's short in spelling itself, right? Short-sightedness. Is that okay? Then we have hypermetropia. So that's what? Long-sightedness. Now for myopia, we said myopia is short-sightedness, right? That's the ability of the eye to see only near objects, right? Okay. Now what do we use to correct it? Concave, God bless you. Do you remember? Concave lens for myopia. Then for hypermetropia, what do we use to correct? Convex lens. We say it's the ability of the eye to see only long distance object but not near. Is that okay? So when is the retina too long or when is the retina too short? For short-sightedness, the retina is too long. For long-sightedness, the retina is too. Is that okay? Okay. Then the next one is yes.
About rod and cone.
He said cone. Cone in the lens, in the retina rather, is used for focusing for adjustment to bright light. Is that okay? So for example, if you are in the dark and power gets restored and your light, your bulb shines. Now you are likely to first do like this, right? And then after a while your eye will now adjust. That is the work of the cone. Is that okay? And of course too, when they take the power too, you see that for a while everywhere will be pitch black. So after a while you can now see images little by little, and after a while, so that one is the rod. Is that okay? So we now have which other thing? Hypermetropia, myopia, conjunctivitis. That one is they call Apollo, right? But the one that naturally comes, astigmatism. So it's a problem with the eyes. The eyes become blurry. Is that okay? Due to old age. Is that okay? Images become blurry in the eye due to old age. While the other one is presbyopia. What is presbyopia? Presbyopia is inability of the eye to focus to accommodate. Is that okay? And this one is corrected by what? Astigmatism. What do you use to correct astigmatism? This one is by cylindrical. Which one is cylindrical lenses? This one, right? Cylindrical lenses. Is that okay? Use it to correct presbyopia. Then astigmatism. Use biconcave lenses. Am I correct? Is what? Astigmatism is what? Cylindrical lenses is astigmatism. Please help us check. Which one? Forward. When you come here. So then it means it will be what? Cylindrical lenses. Is that okay? She's correct, right? So this one is what? Cylindrical lenses, right? And this one is what? Contact lens. Okay, we'll get what it is. Is that okay? So that's that about the eyes. So wait, then for the what about cataract and color blindness? Cataract is not color blindness. Cataract is also due to old age. Cataract is also due to old age, and that's what? Ah, what is in his eyes? Who is Shegun? What is in his eyes? I don't know. I don't know. Let's talk about it later. Is that okay? That's not night blindness. Night blindness. River blindness, not only river blindness. Very please. And know that the diagram, so sometimes you might see, so if you are shown this diagram and then you see ray of light that comes here and then it comes like this, and this is the retina. What's this? What blindness is this? What sightedness is this? This is short sightedness because the image is not touching the retina. The retina is too long. Is that okay? Alright, so the other way will be the one that now comes like this. Now what? Image is focusing at the back of the retina. That word, long sightedness. Alright. Alright, now. So that's that. Then let's talk about the telescope. There are 2 or 3 major types of telescope. We have the compound and the what? The simple telescope and the compound telescope. There's also Galilean telescope now. Galilean. Okay, let's talk about the compound. Let's talk about the simple, and let's talk about the Galilean. So the one thing I remember vividly about this Galilean that they usually ask is about the objective and the focal length. Now, the Galilean and the compound, they are much alike. Is that okay? Because there's also astronomical telescope. Is that okay? And there's terrestrial telescope. The terrestrial telescope is used for seeing objects in Earth. The astronomical telescope is used for seeing objects outside the Earth. So compound telescope has 2 lenses. One that is closer to the object is called the objective. Are you with me now? Then one that is closer to the eyes is called what? Eyepiece. Is that okay? F0 will represent the focal length of the objective lens. F sub E will represent what? Focal length of the eyepiece. So the objective lens for compound distance is less than F0. Is that okay? Than Fe. Is that okay? It means that the lens is closer to the guy. Is that okay? So those are 2 lenses inside one. That's compound telescope. Is that okay? Compound telescope. Is that okay? Then the simple telescope is it called simple telescope or simple telescope? Is that the name? That's the name, right? Because that's simple. The other simple guy refers to basically a magnifying glass. Do you get it? Magnifying glass. Then a Galilean telescope is the opposite of this. Do you get it? It's the opposite of this. And that will be that what? Fe is greater than what? Fe objective eyepiece is less than what? Object. And that makes sense, right? Because you're using it to see objects that are very, very far away. Are you with me? So now, then the magnification of a microscope, of a telescope, is given by magnification due to the objective lens and times magnification due to the. Is that okay? Then of course, if you are told to find the focal length of, do you remember this formula? F sub naught minus F sub E. This is focal length of what? Focal length of what is this? This formula. That will subtract the focal length of the objective piece, my objective length minus focal length of the, what is it? What is this? Okay. These are the basic formulas that you need for calculating that guy. Is that clear? And of course, if you are asked to do calculation with eye defects, it has to do with eye defects. Magnification is going to be V over minus u, something like that. You guys should check your textbook out, especially this minus over minus, no, f sub naught over minus f sub e. Is that okay? For I defective. Is that okay? Are you with me? Alright. So I can't really remember those formulas again. Okay. So let's go to the next thing. What's the next thing, please? Sound waves, right? Or electromagnetic wave. We'll talk about electromagnetic wave a bit now, right? So electromagnetic wave is just a set of waves. Is that okay? It has revox G. The second one is what? Radio wave, infrared wave, X-ray, gamma ray. Infrared, below red, is that okay? Because this one is Roig beam. It's not beam. Roig beam. Then this one below red, above violet. Is that okay? Now, how is light produced? Light is produced like this. We say light is an electromagnetic wave, right? When there is a charge, we know that charge we have electric field around it, a magnetic field around it, right? Charge is electricity, right? And it will have magnetic field around it. We've done that from F equal to what? BVQ. Do you remember? So now, if this charge is now oscillating, we know everything is oscillating, right? So it's moving at a particular speed. So it means that it's oscillating at the speed that is, as a frequency rather, that is equal to speed of light over the wavelength of between here and here. Say wavelength of like 400, for example, 400 nanometers. If you calculate this, that will be the frequency of light. Does that make sense to you now? So it's when a charge is oscillating at that frequency that you see white light. So that's why you are seeing is white light. Does that make sense? All right. So. Now let's talk about this guy. So we know that all the 7 blends give us what? White light. Is that okay? And we do that. We whatever that using Newtonian color disk. Do you remember? So we said Newton's color disk. He said that if you write all the colors, you spin it, you get white, right? So white is not a color, right? And black is not a. So we have red, RGB. Does this make sense? So when you combine this guy and this guy, how do you get it? When you combine this guy and this guy, magenta. What do you guys against guy? Cyan. So, and these guys are called secondary colors. These guys are called. Now, when you now combine a secondary color with a particular, when you combine a primary color with a particular secondary color, that will give you white. What do you call those pairs of color? Complementary. Is that okay? So, for example, which 2 pairs are complementary here? Green and magenta. Which other 2 pairs? Blue and yellow. Cyan and red. Is that okay? All right. So. Okay. Now there's color filter. Color filters are those guys that substances that allow only their color to penetrate. Is that okay? But we absorb other colors. Are we good? Yes. Somebody say T. Okay. All right. The next one. Okay. We are done with the electromagnetic wave. Let's go to sound wave. Are you good? Are we not fast? Okay. So now sound wave. Sound wave is produced by what? Vibrating bodies. Is that okay? Now we know that sound has travels at the speed of what? 330 to 340, right? Yes, sir. Meters per second, right? At room temperature. So it means that temperature affects the speed of sound, right? So that V is equal to what? T. So that V1 over T1 is equal to what? V2 over T2. Does this make sense? Where V is what? Velocity of sound. Where T is what? Temperature. Are you with me? So that's speed of sound. Then we know that sound is what kind of wave? Is a mechanical wave, which means that it requires material medium for propagation. So if it does require material medium for propagation, then it's what? A mechanical wave. There's something I wanted to remember about this sound. Do you know that sound wave? How do you calculate the speed of sound now? Now, how do you calculate this same speed? Let's say talk about the same speed. You calculate the speed of sound by sending a particular sound wave to hit an obstacle and back. You hear it back as what is called what? Echo. Okay, that's reflection of sound. That's called what? Reflection of sound. The echo is what is produced when sound is reflected, right? We call it bounce back. Everybody. So the distance traveled will be two distances between you and the guy. So the velocity of sound what? 2x over t, where x is your distance. Does that make sense? Now the velocity of sound also vary according to the material. Is that okay? So that in air it what? Between this and this. Is that okay? In water it what? 500, no, 1000, no, 500, no, 1000, no, 500, no, 1000, no. So 1500 meters per second. Let's pick the two. Is that okay? Are we all correct? Yeah, correct. So in water, then the speed of sound in steel is what? 5000 meters per second. And there are two types of sound or three types of sound. We have what? Ultrasonic and infrasonic and ultrasonic is audible. God bless you. The one that we can hear is called what? So ultrasonic sound is what? The one that is above the frequency that we can hear. Is that okay? What's the lowest frequency one can hear? 20 hertz. God bless you. And the highest frequency is what? 20,000 hertz. So above, so audible is between what? 20 hertz to 20,000. So this one, infrasonic is what? Below 20 hertz. Ultrasonic is what? Above 20,000 hertz. Are you with me? Who is not with me? Nobody. No. So what is it? Get it? We have to come and dance. Not today, right? Good evening. Oh, yeah. Yeah, sorry. Now, we now have what? Because we've talked about the speed of sound, right? Now, what are these uses of echo? Now, when echo becomes anyhow for a room that has poor acoustic property, what is that called? Multiple reflection of sound. What is it called? Reverberation. God bless you. No. One of the uses of echo is to spot school of fish, right? Using what is called sonars, right? Sonar will pass a sound to the bottom of this thing and then it will be reflected, right? So the reflected ray is what we analyze to check what kind of guy, right? To locate submarines too, right? Okay. So that's that. This guy too uses echo. This animal. Yeah, for mining too. Dolphin, God bless you. And the process is called what? Echo location. It's easy to spot obstacle in front. Is that okay? No. Okay. Now how about refraction of sound? Refraction of sound is what makes sound to be louder in the night than in the day, or travel farther rather in the night than in the day. Does that make sense? Refraction of sound. Okay. Then what else again? I've done reflection of sound, refraction of sound. Refraction of sound. Diffraction of sound, yeah. Diffraction of sound now is when light, that one does not really have any application. But let's talk about Doppler effect. Is that okay? When sound is heard, if a sound is being heard from a moving body, so as it's coming towards you, what will happen to the frequency? It will appear as though the frequency is becoming what? Higher. But if it's going away from you, it will appear as the frequency is what? Becoming lower. What effect is that called? Somebody said Doppler effect. Say Doppler effect. Doppler effect. All right, now you see. Now there's something called beats now. Okay, properties of sound. Thank you. That's what I always remember. Properties of sound. We have the pitch. Somebody say pitch. We have overtone. Is it overtone? We have pitch, quality, intensity first. Let's do intensity first, then quality. Intensity and quality. Now the frequency of sound is what controls the pitch of sound. So do from do, re, mi, fa, sol, la, ti, do. So this do here is going to have a higher pitch than this. Does that make sense? La is also going to have a higher pitch than Do, because the higher you are on the scale, the higher your pitch or the higher your frequency. Does that make sense? Okay, now from here to from do to do is called what? Octave. Do you remember? Anyways, we are not doing music. Now, intensity. So listen now. Pitch does not have any effect on the speed of sound. Intensity does not have any effect on do you understand now? The only thing that affects speed of sound, we said what? Temperature and direction of wind. Is that okay? Direction of wind. That's how you. Is that okay?
Yes, sir.
The intensity now. The intensity of sound is the loudness of sound. And what is that dependent on? So we said this one is dependent on frequency, this one is dependent on what? Amplitude, God bless you. This one is dependent on what? It's dependent on what? Depending on what? Okay. Now, the quality of sound is dependent on the overtones. So which property distinguish between different materials? Different materials is what? Is the quality. And what differentiates them is their what? Overtones. No different material, different musical instruments. And we have three types of musical instruments, right? We have the percussion instruments. Example. Give me one. Do you know it? No. Okay, let's go. That's percussion instrument. Anything you beat is what? We didn't even talk about beat. What is beat? Beat is called by what? Interference of sound. Is that okay? And the frequency of the beat is going to be what? The frequency of the first sound and the frequency of the second sound. That will be the frequency of the beat. Is that okay? It's called by interference of sound. That's why there's what irregularity in the waveform that is produced at the end of the day. Is that okay? No. As we conclude, you see, now there are three types of vibration. We are going to analyze this guy now: overtones and harmonics. Now, there are three types of vibration. We have the forced vibration and the damped vibration. Well, first, we're mentioning musical instruments, right? We said percussion, wind instrument, and what? String. Is that okay? So the wind instruments, e.g., trumpet and all. Is that okay? So this way we analyze their DC. So no. Thank you. Now overtones depend on what is called harmonics. Is that okay? And harmonics also depend on what is called the fundamental frequency. The fundamental frequency, F sub naught, is the lowest frequency that a sound can have. The harmonics is what? Integer multiple of the fundamental frequency. While overtones are what? Any frequency higher than the fundamental frequency. So for a string instrument, now very easily, we just go like this. I'm going to link the video in the description. Is that okay? So we'll stop here for today. No. I made a very explanatory video on this. So I'm going to link the video in the description below. But just to wrap up. So we have the lowest frequency, F sub naught here. This guy has a length, a particular length, right? And I've told you to analyze using what? Wavelength, using pi, right? So we want to analyze this guy using pi. So from node to a node. And here we have antinode, right? So between a node and an antinode, what do we have? Pi over 4. I said pi over 4. Lambda over 4. Between a node and another node is what? Between a node and an antinode is what? Pi over 4. So here what do we have? Pi over 4. Here, what do we have? Pi over 4. Does this make sense? So it means that the total length is going to what? Pi over lambda, over 2. So lambda will have equal to what? 2L. So our F sub naught will have what? V over. You know that F is V over lambda, right? And lambda is now 2L, so it becomes what? 2L. Is that okay? Then the fundamental frequency for wind instrument now. This is for strings, right?
Yes,
and this is for wind instruments. So this one is a close. This one is closed, right? Okay, if this one is closed, this portion will be the what? No, this option what? Antinode. So from here to here is going to what? Lambda over 4. So since L is lambda over 4, then 4 equal to what? I mean L is equal to what? Lambda over 4. Alright, so f sub naught for these guys maybe what?
V over
So from here, lambda will now be equal to what? 4L. So the V over. Does this make sense? All right. So we also know that, lastly, we know that the velocity of a string from sonometer experiment is directly proportional to the what? The tension is the square root of the tension in the string, and is inversely proportional to the square root. Is inversely proportional to the square root of the what? Mass per unit length. Do you remember this? Yes. Mass per unit length. Yes, sir. Then what else? And then we also know that this V is also inversely proportional to the what? What else is the inversely proportional to? We should have 3 quantities now. What's the formula first? Do you remember the formula? V equal to 1 over K root T over M. V is also inversely proportional to what? Can't really remember. No. It's not. A is not in the this for strings. L. V is inversely proportional to what? L. So we introduce L here. Is that okay? And for fundamental frequency, K is equal to what? 1 over 2. So if you are dealing with fundamental frequency, your V will be equal to what? 1 over 2L root T over M. Is this in clear? This N is mass per unit length. So that will be mass over what? Length. Is that okay? That will be our capital M. Are we good?
Yes.
So with this, we come to the end of day 3. Do well to subscribe to the channel and share the video with your friends. I'm going to link the other videos that explain all these parts and solve questions on them more. See you in day 4. God bless you.